Hello there, and welcome back to the Science Sleepy Minds. And tonight you're standing in a place you can't truly stand, looking towards something you can't really look at, in a direction that doesn't even feel like a direction, so much as a weight in the sky. You imagine the Milky Way as a slow river of pale light, and you let your eyes drift toward its thickest, brightest bend, where the stars crowd together like commuters who missed the last train. Somewhere inside that crowded glow is Sagittarius A star, the supermassive black hole at the centre of your galaxy, and in your mind it's less a hole and more a silent mouth held open in the dark. Patient, ancient, and annoyingly hard to photograph. And yes, you probably won't survive this, in the strict sense that you won't survive getting anywhere near it, but fortunately your body is safely in bed, and your curiosity is doing the dangerous part. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, drop your location and local time in the comments, because nothing says community like people around the world collectively refusing to sleep on schedule. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin by walking, not with your feet, but with that inner camera you always carry, the one that can zoom across thousands of light years without filing a flight plan. You trudge through the Milky Way in your imagination, passing constellations like roadside signs. The air in your mind is crisp and thin, the kind of cold you only feel when you're thinking about space too hard. Ahead, the galactic centre glows behind curtains of dust, and that dust is not the cute kind you wipe off a shelf. It's the serious, star-building, light-eating kind, scattered in dense lanes that make the sky look like it's been brushed with charcoal. This is where the James Webb Space Telescope enters like a quiet hero who doesn't do speeches. Not a cape and fanfare hero, more like a librarian who knows where the forbidden book is and doesn't judge you for wanting to read it. JWST is built to see in infrared, which is basically the universe's way of whispering instead of shouting. Where visible light gets blocked by dust, infrared slides through, warm and steady, like a hand slipping under a curtain. You can almost hear Webb's instruments cooling down, hush hush, lowering themselves to temperatures so cold they stop radiating their own heat. Because it's hard to eavesdrop on the cosmos if you keep coughing loudly in the background. And you, in this second-person dream walk, are right there with it. You're not floating in zero gravity with a dramatic helmet reflection. No, you're just present, observing, listening, feeling the scale of the thing you're about to approach. Sagittarius A asterisk, Escar A asterisk if you're on friendly texting terms, is the gravitational anchor of your entire galactic neighbourhood. It's massive, about 4 million times the mass of the Sun, yet in a weird way it's also underwhelming, because it's not currently doing the cinematic black hole thing of devouring stars in a flaming spiral while ominous music plays. It's relatively quiet. Astronomers call it low-luminosity, which is a polite way of saying it's not putting on much of a show right now. But here's the sleepy little twist you're following tonight. Quiet is not the same as nothing happening. Quiet can mean the kind of silence where you notice every tiny sound. Quiet can mean the moment before someone in the other room drops a pan at 3 a.m. Quiet can mean the black hole is snacking lightly instead of hosting a buffet. And JWST, with its infrared sensitivity, is built to notice the snack crumbs. You let your mind settle into the history for a moment, because every great cosmic mystery has a trail of human stubbornness behind it. There's a mainstream historical fact that belongs here like a cornerstone. For centuries, people didn't even agree that the Milky Way was a galaxy. The word galaxy comes from the Greek for milky, and for a long time the Milky Way was simply the Milky Way, a luminous smear. It wasn't until the early 20th century, after fierce debates and better observations, that astronomers accepted the Milky Way as one galaxy among many, an island universe rather than the whole ocean. That shift in perspective is the kind of mental zoom out you're doing right now, except you're doing it from under a blanket, which is objectively the superior way. Now for a quirky tidbit, the kind you can tuck into your pillow like a secret. The centre of the Milky Way sits in the direction of the constellation Sagittarius, the archer. And Sagittarius has been associated with a centaur archer in mythology, a half-human, half-horse figure aiming an arrow. There's something wonderfully weird about imagining ancient sky watchers pointing a mythic bow toward the very spot where a supermassive black hole lurks, as if the night sky has always been hinting in its own symbolic way that something enormous and dangerous lives there. Not that the ancients knew about black holes, of course, but the symbolism is delicious. Like the universe is doing foreshadowing and you're the audience member who whispers, "Oh no, don't open that door." As you move forward, you keep your host voice relaxed because you're here to soothe, not to panic. Still, you can't help letting a little sarcasm curl at the edges because this is science, and science is full of humans, and humans are full of drama. Astronomers spend decades building instruments to measure tiny wiggles in light, and then the universe responds with the cosmic equivalent of a shrug and a faint flicker like, "What? This? Oh, it's nothing." And scientists, being scientists, immediately lean in and go, "It's nothing," suspiciously. You picture the galactic centre as a crowded city at night. Stars are the streetlights, dust is the smog, and gas is the constant traffic. Somewhere in the middle is an intersection so intense that the laws of physics start sweating. Sagittarius, a star itself, isn't visible as an object, because black holes don't emit light in the usual way. What you see is what's around it. Hot gas spiralling, magnetic fields twisting, particles accelerating, flares bursting and fading like camera flashes in a nightclub you absolutely did not want to enter. And this is where that story title you're riding, James Webb finally looked into Sagittarius A star. What it found shocked scientists. Starts to feel less like clickbait and more like a perfectly reasonable description of what happens when you point a ridiculously powerful infrared telescope at a supposedly calm region and discover it's busy. Not busy in a loud, obvious way. Busy in a subtle, twitchy, "Did that just blink at me?" way. You let the idea settle into your body soft and heavy. A black hole can be quiet and still flicker. It can be dormant and still murmur. It can be a sleeping giant that snores in infrared. And of course, because this is the real world and not a neat storybook, there's an open scholarly debate hovering like a thought bubble. Historians still argue whether the term discovery really fits moments like this, or whether it's more honest to say we refine our interpretations as instruments improve. In other words, did Webb find something new, or did it simply give us the sensitivity to notice what was always there? The universe doesn't care what verb you pick, but your species sure does. Now you start to drift toward the first promised clue, the tone-setting hint of what Webb notices. You imagine data arriving not as spreadsheets, but as gentle pulses, like a heartbeat drawn in light. Sagittarius. A star and its immediate surroundings emit infrared radiation, and Webb's instruments can monitor changes over time. When that light brightens and dims, when it flickers, it suggests motion, heating, cooling, acceleration, or shifting density in the material near the black hole. It's the kind of subtle behaviour that makes scientists sit up straighter in their chairs and forget their coffee for a second. Which, if you know scientists, is how you can tell something is serious. Caffeine pauses. That's joke number one, and yes, it's basically a documentary-level joke, but we're keeping it gentle. You keep walking in your mind closer to the centre, feeling that strange combination of calm and threat. The dust lanes part in infrared like curtains in a quiet theatre. You can almost hear the telescope's patient attention, like a long inhale. And in that inhale is your entire premise. You're about to watch the galaxy's heart in a way humans couldn't before. A second joke slips in, light as a feather. If Sagittarius A star is the galactic centre, then the rest of the Milky Way is basically living in the suburbs, commuting around a gravitational downtown that never sleeps. Except downtown doesn't have restaurants. It has tidal forces. The nightlife is complicated. You pause on the edge of what Webb can do and you let your imagination frame the scene in a soothing present tense hush. You are there, you are watching, you are listening to the quietest loud thing in the galaxy. And then, in the data, soft, subtle, undeniable, there is that behaviour, a change, a flicker, a suggestion that the region around Sagittarius A star is more dynamic than the word quiet implies. It's not the kind of shock that explodes the universe, it's the kind that rearranges a scientist's mental furniture. The couch of assumptions gets moved. The lamp of models wobbles. Someone mutters, "huh." And in astronomy, "huh" is basically a scream. Your third joke, just to keep the rhythm, somewhere a black hole is doing something weird, and the entire human species responds by inventing 3 new acronyms and naming the phenomenon after the first person who noticed it while half asleep, which honestly feels like a tradition you might personally relate to right now. You let the flicker linger. You don't explain everything yet. You're not supposed to. You're simply stepping onto the path, your night walk to the galactic centre, where the story will unfold in slow, steady breaths. And as you continue forward, you hold on to the feeling. The Milky Way has a heart, and its heartbeat is faint, irregular, and strangely intimate when you have the right eyes to see it. You keep moving forward from that first faint flicker, like you're following a firefly through a dark hallway, except the hallway is 26,000 light-years long, and the firefly is a gravitational regime that would turn you into a concept. Your inner camera glides closer to the Milky Way's crowded downtown, and you start realizing the first problem. You can't point at Sagittarius A star and say, "There it is," the way you can point at the moon and pretend you're a trustworthy tour guide, because the black hole itself doesn't glow like a lantern. It's more like a missing piece in the puzzle, an absence that explains the shape of everything around it. So you do what humans always do when something won't show its face. You watch how it affects everyone else. You become the kind of detective who never sees the culprit, only the footprints, the bent fence, the startled neighbour, the suspiciously empty cookie jar. And in astronomy, the cookie jar is usually gravity. You drift into the basic, almost magical trick of inference. If you can measure how stars move, you can back-calculate what must be tugging them. This is not new to science. It's practically a family tradition. Mainstream historical fact right here, tucked neatly under your pillow. In 1846, astronomers used irregularities in Uranus's orbit to predict the existence and position of Neptune before anyone actually observed it. They didn't see Neptune at first. They felt it mathematically, like noticing an extra person sitting on your mattress, because the springs complain in a new way. That same logic, follow the wobble, trust the math, becomes the spine of the Sagittarius A star story. So you stand in your mind's eye at the galactic centre, where interstellar dust blocks visible light like thick stage smoke. In ordinary telescopes, that region is like trying to watch a play from outside the building while someone hangs blackout curtains and then parks a truck in front of the door. But in infrared, the curtains thin. The truck becomes less of a truck and more of a vague inconvenience. And with decades of infrared observations from ground-based telescopes, plus adaptive optics, which is basically glasses for telescopes, you can start tracking individual stars whipping around an invisible point. These stars become your messengers. They don't speak in words, they speak in arcs. You imagine them as glowing beads on invisible strings, looping around a spot that seems stubbornly empty. Some of these stars, the famous S stars, swing around so fast and so close that their orbits complete in mere years or decades, not millions of years like the sun's leisurely lap around the galaxy. One star in particular, called S2, becomes a celebrity in scientific circles, an A-list star doing a high-speed red carpet sprint around something it refuses to name. Astronomers track it for years, watching it dive inward, whip around the unseen centre, and fling back out again as if it touched a hot stove. And you, in second person, are right there with the observers, except you're in a softer place. your breathing slow, your eyelids heavy, your brain quietly delighted that the universe can be understood by watching a point of light scoot across the sky. The idea becomes almost soothing. The black hole announces itself by making stars behave oddly. You let your host voice tilt into gentle sarcasm, because it's hard not to. If Sagittarius A star were a person, it would be that one quiet guy at the party who says nothing all night, yet somehow everyone's movement and conversation keeps orbiting him. No, really, the galaxy insists, he's not doing anything. Meanwhile, 4 million solar masses worth of gravity is just sitting there, like it's totally normal. That's joke 1, light and sleepy, like a pillow tossed in slow motion. You slide deeper into the method. To infer the mass of the central object, astronomers measure the orbital period of a star and the size of its orbit, then apply gravity's rules. The tighter the orbit and the faster the star, the stronger the central pull must be. When the numbers come in, they're ridiculous in the best way. Millions of suns crammed into a region smaller than the scale of the solar system. Not spread out mass, not a cluster of normal stars mass, something compact, dense and dark. This is where Sagittarius A star becomes the best suspect long before JWST arrives. You don't need Webb to know something massive is there. You need Webb to understand how it behaves, how it flickers, how it feeds, how it breathes in infrared. Still, the early days of this suspicion were a little messy, because science is always messy at first. You can picture researchers arguing in conference halls and over coffee cups, scribbling on napkins like it's a cosmic crime scene. Some alternative ideas existed. Dense clusters of faint stars, piles of dead stellar remnants, exotic compact objects. But each alternative struggles with stability. A packed cluster tends to collide, heat up, and disperse over time. It can't stay that compact for long without, well, becoming something else. And this is where you get your open scholarly debate line, drifting in like a question you don't have to answer tonight. Historians still argue whether the acceptance of supermassive black holes was driven more by overwhelming observational evidence, or by a kind of theoretical inevitability. Because once the math and the models made black holes useful, the scientific community became extra eager to see them everywhere. Was it pure evidence leading the way? Or was it evidence plus a human appetite for elegant explanations? The universe remains silent on the matter, which is on brand for a black hole. Now a quirky tidbit, something to keep your brain amused while it relaxes. The name Sagittarius A star is a bit of scientific inside joke energy. Sagittarius A originally referred to a radio source in the direction of Sagittarius. Later, astronomers realized there were multiple components, and the compact central one got labelled a star with an asterisk. The asterisk was used in part because it sounded like a star, a playful nod, like the galaxy's centre was getting a little gold sticker for being special. Imagine naming the central monster of your galaxy with something that looks like a footnote. That's joke 2. Humanity discovers a 4 million sun gravitational abyss and responds by essentially saying, let's mark it with a star. We're adorable and doomed. You keep walking through the idea of best suspect and you feel why it matters. It's not just that there's something massive, it's that the mass is concentrated. Compactness is the telltale signature. Like hearing thunder and realizing it's not a far-off storm. It's directly overhead, and you should probably stop holding the metal umbrella. You also begin to sense the difference between knowing it's there and knowing what it's doing. Sagittarius A star is, in many ways, an unusually calm, supermassive black hole compared to the blazing quasars in distant galaxies. Those quasars shine because they're actively feeding. Matter spirals in, heats up, and radiates enormous energy. Our galactic centre, by contrast, seems like it's on a low-calorie diet. But that doesn't mean it's inert. It means the clues are subtle. It means you need sensitive eyes, patient monitoring, and a willingness to be shocked by quiet things. You imagine the observers of past decades, patient people with long nights and colder coffee, tracking star positions year after year. This is slow science, the kind that doesn't fit neatly into your brain's instant results expectation. It's more like tending a garden. You measure, you wait, you measure again. And slowly, the shape of an orbit emerges. The same way you might learn a friend's habits not by one conversation, but by time, by seeing where they always end up, what they circle around, what pulls them back. Now your narrative glides seamlessly into the reason Webb matters. Those stellar orbits give you mass and location. They nail down the centre. They give you confidence. Yes, something enormous is there. But to understand the environment, the hot gas, the magnetic fields, the flare activity, you need different kinds of measurements in wavelengths and sensitivities that past instruments couldn't sustain with the same clarity. And you can feel that you're approaching the moment where the quiet centre starts confessing its small, shocking habits. Because once you know exactly where to look, and once you have the right eyes, even the darkness begins to show texture. You keep drifting forward, toward that invisible point all those stars keep obeying, and your body, safe in bed, lets out a slow breath, as if it too can feel gravity through a story. Joke 3. Soft and late. If you ever feel like your life is chaotic, just remember there are stars out there doing near-relativistic loops around an invisible monster, and they still show up on time, precisely, for decades of observations. Somewhere an astronomer is watching a dot move and whispering, "Good star, very cooperative." Meanwhile, you can't even remember where you put your phone. And with that gentle, drowsy grin in your mind, you continue your approach. You keep that detective feeling from before, the sense that you're learning to see by watching what moves, while your inner walk takes you backward in time for a moment, because the tools you're using tonight didn't appear out of nowhere. They arrive the way all human inventions arrive, slowly, awkwardly, with arguments, funding drama, and at least one person saying, "This will never work," right before it works. You imagine yourself standing on an old stone rooftop observatory, the kind that smells faintly of dust and brass and ambition. The air is colder than it should be, and the sky looks deeper than modern skies because there are fewer city lights and fewer distractions and, let's be honest, fewer smartphones lighting up people's faces like little haunted rectangles. You lean over a wooden rail and look at a telescope that is, by modern standards, adorable. It's like comparing a tricycle to a long-haul freight train. And yet this is where it starts. The mainstream historical fact that anchors this section, steady as a tripod, is that early telescopes in the 17th century, popularized by people like Galileo, transformed astronomy from myth and guesswork into measurement and stubborn, repeatable observation. Suddenly the sky isn't just a storybook, it's an object you can test. Moons orbit Jupiter. Venus has phases. The universe is not arranged purely for your convenience. A humbling discovery, honestly, and one you keep learning every time you try to plug in a USB the right way on the first attempt. You let that old telescope fade, and you slide forward through the centuries. Bigger mirrors, better lenses, better mounts, better clocks, better math. But all along, the galactic centre stays frustrating. It's there. You know it's there. Like a locked room in a house you inherited. You can hear noises behind the door. You can feel a draft. But when you try to open it with visible light, you get nothing but dust. Dust again. The universe's favourite mood lighting. So the story shifts to a newer kind of seeing. Infrared. You picture infrared like warmth made visible, like the ghostly glow of a handprint on glass after someone touches it. Infrared astronomy becomes the trick that lets you peek through cosmic smoke. It's not that dust disappears, it's that dust is less effective at blocking longer wavelengths. The curtain turns sheer. The locked room gets a window. You, in second person, are now walking through a museum of instruments, and each one feels like a different way humans learn to cheat, politely, at the game the universe set up. There are radio telescopes listening to hiss and crackle. There are X-ray observatories catching violent high-energy bursts, and there are infrared detectors, sensitive, fussy devices that need to be kept cold so they don't confuse their own heat with the universe's whisper. This is where the modern look into Sagittarius A star begins to make sense. To look toward the Milky Way's center in visible light is to stare into a sandstorm. To look in infrared is to watch the sandstorm thin until shapes emerge. But it's not simple, because you're on Earth, and Earth is, how do we put this nicely, clingy. The atmosphere absorbs and emits infrared. Water vapor is especially rude about it. It's like trying to listen to a lullaby while someone nearby insists on loudly slurping soup. So astronomers adapt. They build telescopes on high, dry mountains. They send observatories to space. They invent calibration techniques that make you wonder if the real scientific breakthrough is just learning to subtract your own nonsense from the data. Joke one slides in gently. The universe whispers, and humans respond by building a billion-dollar ear, and then spend half the time trying to stop themselves from coughing into it. Now, as you drift through this timeline, you notice a key transition. Ground-based infrared observations start tracking stars near the galactic center with increasing precision. Adaptive optics arrives like a miracle. You picture it as a telescope learning to blink. The atmosphere distorts starlight, making images wobble. Adaptive optics uses deformable mirrors that adjust in real time to counter those distortions. It's like having a telescope that constantly reshapes its own face to keep the view sharp. Creepy, impressive, and honestly relatable if you've ever tried to look awake on a video call. These tools don't just make prettier pictures, they enable long-term measurements. Over years, astronomers map star positions and watch orbital arcs unfold. Your mind returns to those S stars, the ones doing tight loops around the unseen center. Without infrared and without adaptive optics, those stellar tracks would be much harder to resolve. And yet there's always the yearning to go beyond, to see more faintness, to track more subtle changes, to watch the environment around Sagittarius A star itself, not just the stars obeying it. So you step into the era of space telescopes and everything feels quieter. No atmospheric blur, no water vapor, less soup slurping. The view stabilizes, and then the James Webb Space Telescope comes along with its gold-coated mirror segments, its sunshield the size of a tennis court, its whole vibe screaming, "I would like to detect the faintest possible warmth from the deepest possible darkness." Webb isn't just a better telescope, it's a telescope tuned to the wavelengths you need for this particular locked room. Now you let a quirky tidbit curl into the narrative like a little hidden note. Before infrared astronomy became a major observational field, William Herschel, yes, the same Herschel who discovered Uranus, performed an experiment in 1800 where he used a prism to spread sunlight into a spectrum and measured temperatures beyond the red end of visible light. He found it was warmer there, revealing invisible rays we now call infrared. This wasn't cosmic black hole work, but it was the first step in realizing light continues beyond what your eyes can see. The universe has extra channels. Humans just needed the patience to tune in. It's oddly comforting, like realizing the lullaby has harmonies you never noticed. You keep drifting, and you feel how each innovation builds the next. Better detectors, better cooling, better stability, better pointing accuracy, better data processing. And somewhere in that chain are countless people doing unglamorous work. Engineers solving thermal problems, technicians checking vibrations, programmers writing pipelines, scientists arguing over error bars like they're debating the meaning of life, which for them they kind of are. And here comes the open scholarly debate phrase, soft and unresolved, the kind you can fall asleep to. Historians still argue whether the biggest driver of astronomical progress is new technology or new questions, whether we build instruments because we're curious, or whether our curiosity expands because the instruments suddenly make new mysteries visible. It's a chicken and egg argument with a telescope in the middle. You let that debate hover because you don't need to settle it to feel its truth. Tonight, your curiosity and Webb's technology are braided together, pulling you closer to Sagittarius A star. You return to the galactic center in your mind, and now it's less like a blocked view and more like a dimly lit stage. Infrared reveals stars behind the dust. It reveals warm gas. It reveals structures. It reveals motion. And importantly, it reveals time, changes, flickers, flares, variations that happen on human-friendly timescales if you have the sensitivity to catch them. You can almost feel Webb's calm stare, the way it doesn't blink, the way it waits, like a patient night watchman, like someone watching a sleeping animal and noticing its eyelids twitch. Joke 2. The Milky Way's center is the kind of place that makes you want to whisper, "Are you awake?" And the black hole answers by flickering in infrared like, "Mind your business." And because your narrative is meant to glide, you don't stop here. You keep walking forward, past the old observatories, past the first infrared experiments, past the ground-based tracking, toward the moment when Webb's instruments start catching something in the data that feels active. You're still in the same continuous dream, the same night, the same slow approach. You're just better equipped now, carrying centuries of human ingenuity like a lantern that doesn't shine in visible light, but warms the darkness just enough to reveal its shape. Joke 3, last and gentle. If time travelers ever show up and ask what humanity did with its intelligence, you'll have to admit a large portion went into building machines that stare at invisible things and then argue about what the invisibility means. And honestly, fair, it's a solid hobby. You take another slow breath and you continue, letting the infrared curtain part a little more. You keep drifting forward, still following the invisible center the way you'd follow the pull of a magnet under a tablecloth. The dust thins in your imagination, and the scene resolves into something oddly graceful. Not a monster with teeth, but a dance floor. A very expensive dance floor. The kind where one wrong step means physics stops being polite. You watch the stars nearest Sagittarius, a star move with the kind of purpose that makes you feel like your own daily errands are a bit optional. These are the S stars, bright hot stars packed into the central parsec, each one tracing a loop that looks like elegance until you remember the loop exists, because an unseen mass is yanking on them with 4 million suns worth of insistence. You're not seeing the black hole, you're seeing its choreography. It's late, your eyelids feel heavy. But your mind stays awake just enough to track the pattern. An orbit is a signature. An orbit tells you how strong the gravity is, how close the star dares to get, and how tightly the mass must be concentrated. Every sweep of starlight is a sentence in a language gravity invented. And here is the mainstream historical fact that anchors your footing. Johannes Kepler, in the early 1600s, described the laws of planetary motion, elliptical orbits, equal areas in equal times, and the relationship between orbital period and distance. Later, Isaac Newton provided the gravitational explanation that made Kepler's laws feel inevitable rather than mystical. That framework, Kepler's geometry plus Newton's gravity, becomes the old sturdy toolkit you're still using even now to weigh an invisible object at the centre of the galaxy. You're basically using 17th century logic to understand a 21st century telescope watching a relativistic ballet. Human continuity is weirdly comforting. You focus on one dancer, S2. In your mind it glows bluish white, a young massive star that looks innocent the way a sports car looks innocent right before it accelerates. S2 swings around the centre on an orbit that takes roughly 16 years. 16 years? That's not a galactic timescale. That's a you can watch this happen in your lifetime timescale. Astronomers track its position month after month, year after year, and they watch it plunge inward, whip around its closest approach, and rocket back out. The closer it gets, the faster it moves, because gravity isn't just a suggestion down here, it's a command. You let yourself feel the speed, not in numbers but in sensation, a tightening in your chest, a quickening pulse. If you could stand near S2 during its closest approach, don't. Its motion would feel like a silent scream. Your body would not enjoy this. Your atoms would file a complaint. Joke 1, soft and sleepy. You know that moment when you're late and you suddenly walk faster like the sidewalk is going to grade you? That's S2, except the late is about to swing past a supermassive black hole and the sidewalk is space-time itself. Now you notice what the dance reveals. The orbit isn't wide and gentle, it's tight. The pericenter, closest approach, happens at a distance that, in cosmic terms, is uncomfortably intimate. When scientists fit the orbit, the mass required to keep S2 moving like that comes out huge and compact. Not a spread-out cluster, not a fog of matter, something concentrated into a tiny region. And your mind returns to the quiet shock. The center is not empty, it's packed. You also notice that this ballet isn't perfectly Newtonian. Near Sagittarius, a star, gravity gets weird in the way Einstein warned it would. General relativity predicts effects like gravitational redshift, light losing energy as it climbs out of a gravitational well, and orbital precession, an orbit's ellipse rotating over time, like the dance floor itself is slowly turning under the dancer's feet. When S2 whips close, its light shifts. Its motion deviates subtly from a purely Newtonian expectation. These are the kinds of measurements that make astronomers quietly thrilled, because it's one thing to test relativity near the Sun, and another to test it in the deep gravitational pit of a supermassive black hole. It's like comparing a kiddie pool to the deep end where the lifeguard is gravity, and the lifeguard is not paid enough for this. You keep your voice gentle, you keep the cadence slow, but you let the magnitude land. These stars aren't just orbiting something. They're orbiting something so dense that, given what you know about physics, the simplest explanation is a black hole. Now for a quirky tidbit, the kind you can smile at without waking yourself up too much. The S-stars raise an enduring puzzle often nicknamed a version of the paradox of youth. These stars look young and massive, which is strange because the galactic center is a harsh neighborhood. Intense radiation, strong tidal forces, chaotic gas dynamics. It's not the cozy kind of region where you'd expect delicate star formation to proceed normally. Some researchers propose they formed farther out and migrated inward. Others suggest exotic formation scenarios right in the center. Either way, the vibe is, how are you kids even here? The galaxy center is basically a nightclub with a strict dress code, and yet somehow toddlers keep showing up in tiny suits. Joke 2. If you ever worry you're not thriving in a stressful environment, remember the S-stars are out here being young, hot and functional, while orbiting an invisible abyss. Your stress is valid, but the stars are showing off. You watch more orbits, not just S2 but a whole population, S0-102 and others, each one tracing its own ellipse, each one a data point. The more stars you track, the more certain you become about the central mass and its location. It's like triangulating a lighthouse you can't see by watching ships curve around it. And still, because science is never fully satisfied, there's always a corner of uncertainty. Here's where your promised simmering debate creeps in. Historians still argue whether early acceptance of Sagittarius A star as a black hole was a triumph of careful skepticism or an example of scientific momentum, where once the black hole explanation fit, competing ideas were treated as increasingly unfashionable even before every alternative was fully exhausted. In the present, physicists still debate details too. Could some exotic compact object mimic the gravitational pull without an event horizon? Most evidence points strongly to a black hole, but the scientific temperament is to keep a tiny drawer labelled just in case, and never fully throw away the key. You linger on that drawer because it's soothing in a weird way. The universe doesn't demand certainty from you tonight, it just asks you to watch. Now you glide into the what else might lurk nearby question, because the galactic center is not a single actor on an empty stage. It's an entire ensemble cast, all improvising at once. There are clouds of gas, there are filaments of dust, there are massive stars shedding fierce winds, there are probably stellar remnants, neutron stars and black holes of the ordinary stellar mass variety, lurking like background characters in a crowded scene. Some models even predict a cusp of compact objects that gradually sink inward over time, drawn by gravitational interactions. The centre could be sprinkled with invisible heavyweights, each one nudging the dance in subtle ways. So while S2's orbit pins down the dominant mass, small deviations, tiny wobbles, slight mismatches could someday hint at additional companions or distributed mass. Like noticing your bed isn't perfectly still because a cat has decided to reposition itself at the foot. Joke 3. The galaxy's centre is basically your bedroom at night. Mostly quiet, but full of mysterious movements you refuse to investigate because you value sleep and survival. And now you bring that back to the quiet shock you felt in Section 1. Those orbits tell you where to stare. They tell you how big the central mass is. They tell you the location of the gravitational bullseye with extraordinary precision. This is crucial, because when JWST begins monitoring infrared variability, those faint flickers and flares, it needs to know it's watching the right patch of sky, not the cosmic equivalent of the wrong apartment door. You feel the continuity of the narrative. First you learned the centre whispers, then you learned how humans infer an invisible mass. Then you learned how technology peeled back dust, and now you're standing at the edge of the dance floor watching the stars prove over and over that something enormous and compact sits in the middle. And with that proof humming under your skin like a low bass note, you keep moving forward, toward the messier part of the story, where the dance isn't just stars on clean ellipses, but gas and dust and magnetic fields doing their own jittery choreography, the kind that produces flickers in Webb's sensitive eyes. You keep moving, and the star ballet slowly slips behind you like a dream you can still half remember. The clean ellipses, the obedient arcs, the elegant proof. But now you step off the polished dance floor and into the alleyways behind the theatre, where the real mess lives. This is the part of the galactic centre that smells, metaphorically, like warm metal and static electricity. Not because space has air, don't be that person in the comments, but because your brain needs a texture for violent physics happening quietly. Ahead is the central molecular zone, the Milky Way's most crowded pantry of gas and dust. And you realise something crucial. Feeding a black hole is not like pouring water down a drain. It's more like trying to toss spaghetti into a spinning fan and then acting surprised when dinner becomes an art installation. The black hole wants mass. Gravity always wants mass. But the universe is stingy about handing it over neatly. You float through clouds of molecular hydrogen, carbon monoxide, ammonia, cold stuff by cosmic standards, but still restless. The gas is clumpy, filamentary, turbulent. Some of it forms stars, some of it gets shredded by radiation, some of it gets stirred by shock waves, and all of it is moving, colliding, cooling, heating, compressing, expanding, like the galaxy is constantly kneading dough it can't quite bake. Here's your mainstream historical fact, slipped in like a steady heartbeat. In 1687, Newton's Principia formalised gravity as a universal force, and that idea eventually let astronomers understand why gas doesn't simply fall straight inward. It carries angular momentum, the cosmic equivalent of momentum that refuses to let go. So instead of dropping cleanly into the centre, it tends to orbit, swirl, and form structures. In other words, the reason Sagittarius A star isn't constantly gulping everything nearby is the same reason you can't just walk straight into a spinning merry-go-round without something weird happening to your knees. So you look at the environment near Sagittarius A star, and it's less a tidy accretion disk and more an ecosystem. Stellar winds from massive stars blow like constant hairdryers set to aggressive. Supernova remnants leave behind expanding shells and hot plasma bubbles. Magnetic fields thread through the region, twisting and snapping like invisible rubber bands. And the dust, oh, the dust doesn't just block light. It shapes chemistry. It shields cold pockets where molecules can survive. It helps form stars. Dust is basically the galaxy's habit of keeping secrets in plain sight. You drift past a few named features the way you drift past neighbourhoods in a nighttime taxi. The circumnuclear disk, often described as a ring-like structure of molecular material, sits not too far out on the galactic scale, like a messy belt of gas that may or may not be feeding inward efficiently. Closer in, there's hot ionized gas and streamers, sometimes described as a mini-spiral, swooping around like glowing ribbon caught in a slow whirlpool, and you can feel why this matters for Webb's later shock. Because if the centre is quiet, it's not quiet because nothing is available. It's quiet because the process of delivering food to a black hole is complicated, inefficient, and chaotic. The black hole is surrounded by ingredients, but the recipe keeps failing. Joke 1. Gentle. Sagittarius. A star lives in the middle of the galaxy's fridge and still manages to act like there's nothing to eat. Relatable, honestly. You watch how gas might migrate inward. Some of it loses angular momentum through collisions, friction, turbulence, or interactions with magnetic fields. Some of it gets captured by the black hole's gravitational influence, but even then it doesn't drop straight in. It heats up, forms a hot, tenuous flow, and radiates in different wavelengths. The act of falling becomes a conversion, gravitational energy into heat, into light, into motion. But Sagittarius A star is a low-luminosity black hole. It's underfed. It accretes at a tiny fraction of what it could if it were gorging like a quasar. That raises a question that keeps scientists awake, though you tonight will keep it drowsy. Where is the missing energy? Where is the missing light? Is the gas not reaching the event horizon? Is it being blown away by winds? Is the flow radiatively inefficient, storing energy in particles and magnetic fields rather than shining brightly? This is where your open scholarly debate phrase slides in, as promised, like a soft argument you can half ignore. Historians still argue whether the quietness of Sagittarius A star should be framed as a special mystery of our galaxy, or as a common phase most supermassive black holes spend their time in, because the dramatic blazing phases might be brief, while the long boring stretches dominate cosmic history. In other words, are we lucky to live next to a sleepy giant, or is the giant usually sleepy and we just happen to catch it on a calm night? You let that sit. It's calming in a way to imagine the universe spends most of its time not screaming. Now for a quirky or fringe tidbit, something a little odd, a little flavourful, but not so wild it wakes you up. There have been speculative ideas over the years that the central regions of galaxies could host not just simple gas inflows but strange, transient structures, like dense clumps that survive longer than expected, or intermittent rain of cooled gas blobs that drop inward in bursts. Some people have even played with the poetic notion that accretion can happen in lurches. The black hole is quiet, 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 and then it gets a mouthful. Not a steady diet, but a series of midnight snacks. It's not the mainstream picture in its most cartoonish form, but the underlying idea, episodic feeding, keeps showing up in models because turbulence and feedback rarely produce steady anything. The galaxy doesn't do smooth. The galaxy does mood swings. You continue your sensory glide. You imagine the gas as a slow fog with hidden currents. You imagine magnetic fields as lines you can't see but can feel, like silk threads tugging at charged particles. You imagine shock fronts where winds collide, compressing gas and heating it, leaving behind hot spots that could later glow in infrared. And now you understand why Webb's ability to monitor faint changes matters so much. In a chaotic region, the most honest clue is time variability. If something brightens, something changes. Density, temperature, magnetic configuration, particle energy. A flare is not just a pretty flash. It's a diagnostic, like a hiccup that tells you the digestive system is doing something. Joke 2. Scientists love flares because they're basically the black hole's way of posting, "I'm fine," at 2 a.m. And everyone immediately assumes something is very much not fine. You keep moving closer in your mind, and the environment shifts from cold, molecular gas to hotter plasma, ionized material where electrons and ions are separated, dancing to electromagnetic rules as much as gravitational ones. This is the realm where magnetic reconnection becomes plausible. Field lines twist, tangle, snap, and release energy, like cosmic Velcro ripping open in slow motion and spraying heat into nearby particles. But you don't rush into the flare physics yet. You simply lay the groundwork. The galactic center is messy, and mess produces surprises. A low feeding rate doesn't mean no feeding. It means the black hole is living off crumbs, drips, and occasional bursts, and those bursts can show up as the flickers Webb notices. You glance back mentally at those S-stars, clean orbits in a dirty neighborhood. The contrast is striking. The stars give you geometry and certainty. The gas gives you chaos and interpretation. It's like measuring the walls of a room precisely, then trying to predict what a cat will do inside it. The room follows physics. The cat follows vibes. Joke 3, soft. If Sagittarius A star were a pet, it would be the kind that ignores the expensive food you bought and then suddenly tries to eat a plastic bag at 3 a.m. You're not mad, you're just exhausted. And now, without breaking the glide, you let the final thought of this section settle in. The Milky Way's centre is not a vacuum with a black hole stamped in the middle. It's a living, crowded, turbulent zone where dust hides, gas swirls, stars blow winds, and gravity conducts the whole orchestra. Webb is about to listen closely enough to hear the quiet parts, the tiny changes that say, something just happened near the edge of the void. You keep floating forward, following the currents toward the instruments that can catch those whispers. You keep drifting forward from the galactic center's messy pantry of gas and dust, and now the feeling changes. The environment is still chaotic, still crowded, still doing its best impression of a stirred-up snow globe, but your attention narrows like you're bringing a calm, careful finger to your lips. Because this is the moment you meet the listener, the watcher, the gold-foiled eavesdropper parked far from Earth's heat and chatter. You step up beside the James Webb Space Telescope the way you might step beside a huge, silent animal at rest, respectful, a little awed, and trying not to make sudden movements even though nothing here has air to carry your clumsy noises. Webb is not shaped like the telescopes you grew up drawing as a kid. It's not a tube. It's a set of honeycomb mirror segments arranged like a futuristic flower, and behind it a layered sun shield stretched wide, a shimmering kite designed to keep the whole machine cold enough to hear the universe whisper. And you can almost feel what cold enough means. Not the cozy cold of flipping your pillow to the other side. This is the engineered cold of survival. Temperatures low enough that Webb's own warmth won't drown out the faint infrared glow of distant dust, dim stars, and, importantly tonight, the subtle, restless emissions from the region around Sagittarius A star. You settle into the sensory idea. The telescope isn't just looking, it's listening in light. Here's the mainstream historical fact you tuck in, gentle and steady. In 1990, the Hubble Space Telescope launched and changed how humanity saw the cosmos, not because space is inherently magical, but because getting above Earth's atmosphere removes a huge amount of distortion and absorption. Hubble made Space Telescope feel like a permanent upgrade to your species' eyesight, and Webb is that same tradition, but tuned to different wavelengths, infrared instead of primarily visible and ultraviolet, built to see what Hubble can't, especially through dust. The baton passes, the orchestra continues, and you're the drowsy audience member who somehow got front row seats. Now you drift closer to Webb's personality, because yes, instruments have personalities when you spend long enough with them. Webb is fussy, Webb is precise, Webb is the kind of machine that demands planning, scheduling, calibration, and patience. You can't just shout, "Hey Webb, look at the galactic center real quick." Webb wants to know what filter, what exposure, what cadence, what pointing constraints, what thermal limits, what background subtraction plan. It's like asking a world-class chef to make you toast and being handed a 3-page questionnaire about bread hydration. Joke 1. Soft. Webb is not point and shoot. Webb is submit your application and wait for approval. And yet, that fussiness is exactly why it's powerful. Webb's instruments are designed to detect faint infrared signals with exquisite sensitivity. You picture those instruments, NIRCam, NIRSPEC, MIRI, as different kinds of senses, one for imaging, one for splitting light into spectra, one for longer wavelength mid-infrared, each one giving you a different angle on the same truth. Webb doesn't just show you a pretty picture, it can tell you what the light is made of, how hot something is, how it changes over time. You pause on time because time is the secret ingredient in this story. Astronomers already know where Sagittarius A star is, thanks to those S-star orbits you watched earlier. They already know the mass is huge and compact. But the environment around it, hot plasma, magnetic fields, infalling material, is not something you capture once and frame on the wall like a family photo. It's something you monitor like a sleeping person's breathing. Tiny changes matter. Flickers matter. Short, subtle flares matter. Webb is built to notice those quiet changes. You imagine the telescope's sunshield like a giant hand held up against the sun, blocking glare and heat. It's not romantic exactly, but it's intimate in a technical way. The universe is faint, and to hear it, you must become quieter than your own equipment. Webb becomes quiet on purpose. The telescope cools, the detectors settle, the noise floor drops, and suddenly, faint infrared variations that would have been buried before can rise like little ripples on a dark pond. Now for your quirky tidbit, something odd but true to vibe. The Webb telescope's mirror is coated with a thin layer of gold, because gold reflects infrared light extremely well. So in the most literal sense, you're using a gold mirror to look into the galaxy's darkest heart. Humanity's most ancient symbol of wealth and desire, gold, repurposed into a calm scientific tool aimed at a place that does not care about your economy. There's something quietly hilarious about that. The universe has black holes. Humans bring jewellery. Joke 2. If aliens ever audit us, they're going to find it deeply suspicious that we covered our space telescope in gold and then insisted it was for infrared reflectivity. Sure, Jan. You keep moving, and your mind gently touches the logistics. Webb sits far from Earth, positioned so that it can keep its sunshield properly oriented, staying cold and stable. Stability matters because you can't measure tiny flickers if your instrument is jittery. It's like trying to detect a whisper while riding a motorcycle. You need calm, you need control, you need the cosmic equivalent of turning off the dishwasher, and Webb gives you that calm. But here's where the narrative gets deliciously sleepy and slightly ominous. When you build a tool sensitive enough to detect faint variable infrared light from a quiet, supermassive black hole, you're essentially asking the universe to show you its subtle habits. And the universe, being the universe, sometimes answers by revealing that your categories, quiet, dormant, inactive, were more about your expectations than about reality. You let that thought hang there, like a slow pendulum. Now comes the open scholarly debate phrase, because even the story of Webb itself has human arguments baked in. Historians still argue whether the greatest space observatories are primarily triumphs of engineering persistence or of political persistence, whether they succeed because the science is compelling, or because enough people fought hard enough for long enough to keep the project alive through delays, redesigns, and budget battles. You can feel the truth of that without needing to pick a side. Webb exists because humans are stubborn. Sometimes that stubbornness is exhausting. Sometimes it opens the universe. You continue forward, letting Webb's listening quality become the mood of your own narration. Your voice slows. You speak as if you're standing in a dark control room, with screens turned down low. The data doesn't come as fireworks. It comes as numbers, as curves, as faint rises and falls. It comes as the soft awareness that something at the galactic centre is changing while you watch. And this is where you, second-person traveller, begin to appreciate how different this is from the old way of looking. Old observatories gave you snapshots. Webb can give you something closer to a heartbeat monitor. Not perfectly, this is astronomy, not hospital, but close enough to make the metaphor stick in your drowsy mind. You imagine a timeline of the light, infrared brightness on the vertical axis, time on the horizontal axis. The line should be mostly flat if the source is steady, but near Sagittarius A star, the line wiggles, it twitches, it rises, dips, pauses, and rises again. Quiet, yes, but not still, not asleep. More like a person trying to sleep, shifting under the blanket, turning their head, dreaming intense dreams. Joke 3, barely above a whisper. Sagittarius. A star is quiet. The way you're quiet when you say you're going to bed and then spend 40 minutes thinking about something embarrassing you did in 2013. You let yourself feel the scale again. 4 million solar masses, a region so compact that stars sprint around it. A surrounding environment of turbulent plasma and dust. And now an infrared telescope so sensitive and cold that it can catch subtle fluctuations, little flarelets, changes in emission, hints of processes happening close to the black hole's edge. The entry of Webb is not a new beginning, it's a sharpening. The same mystery brought into finer focus, the same locked room, now with a better key, and as you continue forward, you can sense you're approaching the moment when finally looked becomes finally noticed, and quiet becomes quietly shocking. You remain in motion, the narrative unbroken, gliding toward the first Webb stare into the galactic centre itself, toward the initial expectation of calm, and the first hints that calm is just a thinner kind of storm. You stay right beside Webb, close enough in your imagination to sense the stillness of its posture, the way it holds its mirror toward the Milky Way like a calm, unblinking eye. And now the target isn't the broad, romantic notion of the galactic centre. Now it's a specific patch of sky, a carefully chosen field where the coordinates are no longer a guess, because the S-stars already told you where the gravitational bullseye sits. You're not wandering anymore, you're aiming, so you let yourself settle into what astronomers think they're about to see. Sagittarius A star is famously underdramatic compared to the blazing cores of distant galaxies. It doesn't roar like a quasar, it doesn't flood the sky with radiation. It's the kind of supermassive black hole that makes you say, with a tired shrug, well, it's there. Like an old appliance that still hums but never does anything exciting, until the night it starts making a new sound and you sit bolt upright whispering, oh no. That's the vibe as Webb begins to watch. The first Webb glimpse in your mind is not a single glorious snapshot, it's a sequence. It's watching the same region over and over, letting time become a microscope. Webb's near-infrared instruments, those exquisitely sensitive eyes, collect light that has threaded through dust lanes and arrived at the telescope like a slow confession. The data isn't cinematic. It's a stream, a gentle rain of photons tallied into numbers, and at first you expect modesty, you expect quiet. Because quiet is what Sagittarius A star has been historically in the modern observational era. A low-luminosity source, a central engine that seems to be sipping rather than gulping. That's your mainstream historical fact for this section, woven softly into the present. For most of the 20th century, the centre of the Milky Way was primarily studied through radio observations. Sagittarius A was identified as a strong radio source, and the compact component we call Sagittarius A star became the focus once higher resolution radio techniques developed. The galactic centre, in other words, was first voiced to us in radio, before it ever became a clear infrared stage. Humans learned its name from static, before learning its silhouette from starlight. So Webb's team goes in with that history humming behind them. They're not expecting fireworks, they're expecting a faint glow, maybe occasional small flares, the kind you could attribute to routine turbulence. A sleepy dragon maybe, but still asleep. You too are trying to stay sleepy. You're letting the narrative flow like warm tea. But you also feel the tension in the premise, because this story exists precisely because the first look isn't as boring as the word quiet implies. The earliest moments of monitoring have a strange intimacy. You imagine the infrared scene, a crowded background of stars, many of them bright and young, clustered toward the centre. Dusty structures lurk like smoky ribbons. And somewhere in the clutter is the emission associated with the immediate environment of Sagittarius A star. Not the black hole itself, but the hot material and energetic processes near it. The neighbourhood where magnetic fields twist and particles get accelerated into brief luminous tantrums. You watch the light curve in your mind again, the line that should behave, the line that should mostly stay level. At first it does what it's supposed to do. You almost relax. You almost let your brain say, see, quiet, nothing to worry about. The same way you glance at a sleeping pet and think, all good, right before it makes the weirdest noise you've ever heard. Then the line changes, not violently, not like a supernova, but it starts to act weird. Little rises, little dips, flickers that seem too structured to dismiss as random noise, the kind of behaviour that makes a careful scientist lean closer to the screen and a sleepy listener feel a small, delicious chill. And here's your first gentle joke of the section. The universe is the only place where it's probably just noise can turn into a decade-long research program with a funding proposal, a dozen co-authors, and a new acronym that sounds like a sneeze. You let the flicker become the centre of attention, but you don't over-interpret yet. You remember how messy the environment is. You remember the central molecular zone's turbulence. You remember stellar winds and shock fronts. You remember magnetic fields threading through plasma. In such a place, variability is expected, but the specific pattern, the frequency, the time scale, the amplitude, those are the clues that start to tug at the edges of what expected means. Some of the flickering looks like a slow breathing, a rise over minutes, a fall, then another rise. Other moments pop brighter, then fade, like a match struck and immediately waved out. And Webb's advantage is that it can see these changes with clarity, because it's quiet itself, cold, stable, far from Earth's warm interference. You begin to feel the shift from we're confirming what we know to we're learning something new. That shift is often where shock lives in science. Not the shock of exploding assumptions, but the shock of realizing your assumptions were too simplistic. The black hole isn't quiet, it's subtle, it's doing small things often. Now you slip in your quirky tidbit, the kind that feels like a strange garnish on a serious meal. Sagittarius. A star has long been a playground for speculative storytelling among physicists and science communicators because it's close enough to study and mysterious enough to invite imagination. Over the years, you'll find fringe-flavoured chatter about everything from hidden orbiting objects to exotic compact alternatives. Ideas that usually don't survive the full weight of evidence, but persist because the centre's complexity makes it feel like a place where almost anything might be hiding. The galactic centre is the universe's messy drawer. You know it's mostly normal stuff, but you can't shake the fear there's a weird battery rolling around in there. Joke 2. If Sagittarius A star were a kitchen, it would be the one drawer where you keep scissors, take-out menus, mystery keys, and one spoon you're pretty sure isn't yours. Scientists open it carefully. Now for the open, scholarly debate phrase. Soft, unresolved, and perfectly suited to a sleepy mind. Historians still argue whether the public's fascination with black holes has subtly shaped the way discoveries get framed, pushing researchers and communicators toward dramatic language, even when the real excitement is in careful statistical patterns and gradual model improvements. In other words, is it the data that shocks, or the human urge to narrate the data as a plot twist? The truth is usually both, braided together. But tonight you stay with the experience as it happens. You're watching Webb watch the centre. The initial expectation of modest behaviour starts to fray. The variability seems persistent, not a one-off flare you can shrug away as cosmic indigestion. More like a continuous low-level restlessness with occasional stronger flares rising above it. If Sagittarius A star were a person trying to sleep, it wouldn't be peacefully unconscious. It would be half awake, shifting, dreaming, sometimes jolting, then settling again. And this is where the finely looked part matters. Earlier telescopes could catch big events, or they could look with lower sensitivity, or they could struggle with atmospheric interference, or they couldn't maintain the same steady gaze. Webb can sit there and keep listening in infrared, letting patterns emerge from repetition. Patterns are what turn flickers into physics. You imagine a scientist's mind doing what your mind is doing, but faster and with more spreadsheets, measuring timescales, correlating brightness changes in different bands, checking whether the apparent variability could be contamination from nearby stars, calibrating out instrumental effects, comparing with previous observations, the careful paranoia of good science. Because the worst-case scenario is not the black hole is boring. The worst-case scenario is you discovered a calibration bug and accidentally published it. Joke 3 gently. Every astronomer's nightmare is that the universe didn't do something surprising. Your instrument did, and it's about to become famous for the wrong reason. Still, the flicker persists. It's not going away when you cross-check. It's not smoothing out when you average. It's sitting there in the data like a quiet tapping from inside the locked room. And as you continue drifting forward, you hold on to the feeling that something at the centre is more active than the label low-luminosity suggests. Not brighter than a quasar, no, but alive enough to keep making signals. Alive enough that the next step, following the more dramatic variability, the stronger flares, the suspicious hints of rhythm, will feel like a genuine surprise. You remain calm, you remain sleepy, you keep your eyes half-lidded, but you don't look away. You keep your gaze on that twitchy little light curve, the one that's supposed to behave, the one that's supposed to be the astronomical equivalent of a sleeping cat. Still, predictable, maybe a gentle rise and fall if it's breathing deeply. But now it's not breathing. It's tapping its foot. It's drumming fingers on the table. It's doing that thing where someone says they're fine and then cleans the entire kitchen at midnight with unsettling energy. The flicker sharpens into something you can't politely ignore. There's not just a single flare either. You watch multiple brightenings ripple through the infrared record, some modest and some brighter, and the shock isn't that Sagittarius A star can flare. Astronomers already knew it could, from earlier infrared and X-ray observations. The shock is the frequency and the texture of the variability as Webb stares with that cold, patient sensitivity. The centre doesn't merely hiccup once in a while, it fidgets, constantly. Like a quiet heart that turns out to have a surprisingly busy rhythm when you finally put the stethoscope on properly. You're still moving forward, still in second person, still safe in bed, but your mind is now hovering close to the black hole's neighbourhood, like you're leaning over a railing and watching sparks rise from a dark street far below. Every flare is a clue, every flare is a message written in heat and timing. And yes, this is where scientists start swallowing hard. Because flares mean energy is being released, and near a black hole, energy release is a whole genre of weird. You're dealing with plasma, ionized gas where electromagnetic forces matter as much as gravity. You're dealing with magnetic fields that can twist, knot, and snap. You're dealing with particles accelerated to absurd speeds, then cooling and dimming in patterns that your sleepy brain can almost feel as a rise and fall tide. Mainstream historical fact, woven in gently so it doesn't jolt you awake. In 1915, Einstein's general theory of relativity reframed gravity as the curvature of space-time, and black holes became a natural consequence of that framework, even before any were confirmed observationally. The key point for your flare story is that near a black hole, gravity doesn't just pull harder, it warps time and paths and energy budgets in ways that make ordinary intuition start filing resignation papers. When modern astronomers see rapid flares near Sagittarius A star, they're watching physics operate in a regime Einstein helped predict, even if he personally wasn't thrilled about black holes as literal objects. You let that sink in, softly. The flares aren't just fireworks, they're near-horizon behaviour, the kind of behaviour that happens where space-time is steep. Now the shocked scientist part. You watch how Webb's continuous monitoring reveals that the infrared emission is not steady with rare outbursts. It's more like a baseline of restless variability punctuated by larger flares, like an ocean that's never truly calm, even when the surface looks smooth from far away. And some flares rise and fall on short timescales, minutes to tens of minutes, suggesting the emitting region is compact. Small regions can change quickly. Big regions can't, not without sending a memo to causality first. So the brain of the scientific community starts doing its favourite hobby, turning timescales into sizes. If a flare doubles in brightness quickly, the region producing it can't be larger than the distance light can cross in that time. You don't need to solve equations tonight. You just feel the principle. Fast flicker means small source. Small source means close in. Close in means the black hole's immediate environment is actively reorganizing itself. You imagine a little hotspot, a blob of plasma heated or energized, orbiting near the black hole. It glows brighter, then dims, maybe because particles cool, or the blob shears apart, or it rotates out of the best viewing geometry. Another flare follows, then another. Some seem almost rhythmic, as if something is orbiting and reappearing, like a lighthouse beam sweeping past. And there it is, the hint of rhythm. The kind that makes scientists go quiet, not relaxed quiet, but everyone stop talking, I'm counting, quiet. Because rhythm suggests structure, orbiting material, repeating processes, magnetic cycles. It suggests you're not just watching random turbulence. You might be watching something like a pattern. Joke 1. Featherlight. This is the part where astronomers become the world's most sleep-deprived drummers, trying to decide if the universe is keeping time or just accidentally doing jazz. But of course you don't settle too quickly into the comfort of a neat orbiting hotspot, because the galactic centre is allergic to neatness. The same data could be explained by magnetic reconnection events that occur repeatedly but not periodically, like snapping rubber bands in a tangled drawer, or by turbulence in the accretion flow producing bursts as clumps collide and heat, or by shocks propagating through plasma, or by multiple small regions flaring at different times, blending into a light curve that only looks like rhythm when you want it to. And this is where your promised open scholarly debate phrase glides in, a soft pillow of uncertainty. Historians still argue whether apparent periodicities in astronomical data are more often genuine physical clocks or artifacts of human pattern hunger, because when you stare at enough noise, your brain starts begging to hear a beat. In the case of Sagittarius A star, researchers debate which features are robust and which are statistical mirages, especially when the environment is complex and the monitoring windows are limited. You keep that debate unresolved because it belongs here. It's part of the shock. Webb sensitivity gives you more detail, but more detail also gives you more ways to argue. Now, a quirky or fringe tidbit, something strange enough to be fun, but not so strange you sit up. Black holes have long inspired speculative ideas about black hole clocks, not in the sci-fi time travel sense, but in the sense that orbiting hotspots near the innermost stable regions could, in principle, act like repeating signals that encode spin and geometry. Some enthusiasts go a little too far, imagining stable, long-lived beacons circling forever. In reality, near Sagittarius A star the flow is likely turbulent, and anything like a hotspot might be short-lived, more like a spark on a windy night than a lighthouse built of stone. Still, the concept that timing might reveal black hole properties is one of those ideas that keeps returning, because it's too elegant not to try. You stay with the sensation of it. Webb doesn't just see a flare, Webb sees multiple flares. Webb sees them often. Webb sees that the so-called quiet black hole is more like a simmering pot with occasional bubbles breaking the surface, and you can picture the scientist reacting in that very scientist way, not screaming, not fainting, but getting intensely polite and intensely alarmed. More meetings, more cross-checks, more coordination with other observatories, more people muttering, "We need more monitoring," which in astronomy is the equivalent of saying, "I have seen enough to know I haven't seen enough." Joke 2, softly. The universe hands scientists a mystery, and scientists respond by asking for more telescope time, the way a kid asks for 5 more minutes on the playground. Except the playground costs millions of dollars and the slide is space-time, you also begin to sense the stakes. Sagittarius A star is the nearest supermassive black hole. It's your local specimen. If you can understand its flare physics, why it brightens, how it dims, what the timing implies, you're not just learning a fun fact about the Milky Way, you're building a template for interpreting faint, low-luminosity black holes in other galaxies, the ones you can't watch in such detail. But Webb is showing that low luminosity doesn't mean low activity. It means the activity is subtle and often hidden in wavelengths you need the right tool to measure. Your attention lingers on the nature of shock itself. Shocked scientists doesn't have to mean they expected nothing and got everything. It can mean they expected occasional flares and got a constant jitter. It can mean they expected randomness and got hints of structure. It can mean they expected a sleepy giant and found a restless one. You let the variability feel personal, because you're in second person and the narrative is meant to be intimate. You imagine you're watching a campfire from far away. Most of the time it glows steadily. But then a pocket of resin pops, sending a bright spark up. Then another. Then several in quick succession. The fire was never off. You just weren't watching closely enough to notice how alive it was. Joke 3. Quiet as a yawn. Sagittarius. A star is the kind of quiet roommate who says they're going to bed early, and then you hear them reorganizing their entire closet at 1:37 a.m. in complete silence somehow, which is honestly the most unsettling part. You don't jump ahead to explanations yet. Those are coming. For now, you stay with the raw discovery feeling. Webb's stare turns quiet into restless. The flares are real. The flickers are frequent. The galactic center is not a static background. It's a living, changing system, and you've just watched it blink. You keep drifting forward, letting that blinking guide you toward the next question your sleepy mind can hold. What exactly is causing those sparks? Hot spots, magnetic knots, turbulent clumps, and why do they behave the way they do? You stay with the sparks you just watched, those quick brightenings, those soft collapses back into dimness, and you let your mind do what it naturally does at night. It starts trying to explain a sound you can't quite locate, like hearing a faint thump in the walls and deciding whether it's the house settling, the neighbour's cat, or your own heartbeat being dramatic. Near Sagittarius. A star, every flare is a thump in the walls of space-time. So you lean in, still second person, still present tense, and you begin sorting through the best suspects the way astronomers do. Patiently, suspiciously, and with the deep awareness that the universe is under no obligation to pick just one culprit. The first suspect is the simplest to picture, a hotspot. You imagine a small blob of plasma, charged particles, mostly electrons and ions, getting suddenly heated or energized in the inner accretion flow. It brightens in infrared as the particles radiate, then dims as they cool or disperse. If this hotspot is orbiting close to the black hole, it can produce variations that seem patterned, because the orbit brings it into and out of favourable viewing angles, and because relativistic effects can boost or diminish its brightness. It's like watching a glowing ember being carried around on a carousel. Sometimes it swings closer, sometimes it swings away, and your eyes interpret that as a rhythm. But the second suspect is more twitchy, more electric, more like the universe playing with tangled chords, magnetic reconnection. You picture the magnetic field lines near Sagittarius A star as invisible strands woven through the plasma. In a turbulent flow, those strands get twisted, braided, and kinked. Sometimes the braids snap and reconfigure, reconnection, releasing stored magnetic energy suddenly into the particles. That energy can accelerate electrons to very high speeds, and as those electrons spiral and jitter in magnetic fields, they radiate. A flare can be the brief signature of a magnetic knot popping loose, and it's not a calm pop. It's the kind that says, a lot of energy was stored here, and now it isn't. Mainstream historical fact tucked in gently, the concept of magnetic reconnection rose to prominence in space physics because it helps explain rapid energy releases in phenomena like solar flares, which have been observed and studied for well over a century as telescopes and spectroscopy improved. The sun, in other words, is your local training ground for understanding how magnetic fields can store energy and then dump it suddenly into heat and radiation. When you talk about reconnection near Sagittarius A, you're borrowing a mechanism with a solid history in heliophysics, only you're applying it in a gravitational deep end where the pool rules change. You let that comparison soothe you. It's familiar. Solar flares are dramatic, but they're not alien. They're physics doing a fast trick. If the sun can do it, a black hole's neighbourhood, full of plasma and fields, can do it too, just with different scales and different constraints. Joke 1, sleepy. The sun throws tantrums with fire, Sagittarius A throws tantrums with math. Now, there's a third suspect that doesn't require a single event, like a snapping magnetic field line. It requires only the relentless chaos of a flow that can't decide what shape it wants to be, turbulence and shocks. In the messy accretion environment, clumps of gas can collide, density waves can compress material, small shocks can heat pockets briefly. The result is a series of brightenings that look like flickers, not because something snapped, but because the plasma is constantly bumping into itself, reheating, cooling, and rearranging. Think of it as the black hole's neighbourhood being a perpetual construction site where someone keeps dropping a toolbox not once but repeatedly, and always when you're trying to sleep. And then there's the fourth suspect, which isn't separate from the others so much as it's a consequence of them. Outflows and tiny jets. Even quiet black holes can produce winds, streams of particles and magnetic energy flowing outward. Some models suggest that in low-luminosity systems like Sagittarius A, a significant fraction of inflowing material might not make it all the way in. It can be heated and driven back out. If so, the flare activity might be tied to episodes where energy gets channeled into these outflows, briefly changing the emission. You notice how every explanation has the same underlying theme. The region is active and the activity is intermittent. It's not steady burning, it's sparks, bursts, and pulses. Now for your quirky tidbit, the kind that feels like a strange seasoning. There's a long-running, semi-poetic habit among some astrophysicists of describing the inner flow as a kind of cosmic weather. Storms of turbulence, magnetic squalls, and pressure fronts. It's not fringe as in unscientific, but it is quirky in its imagery. Accretion as meteorology. If you accept the metaphor, then flares are lightning. Sudden, localized energy releases in a charged, churning medium. You can almost hear the lullaby version of that idea. The black hole's neighbourhood is stormy, even when the overall climate looks calm. Joke 2. Your galaxy's centre has weather, and of course it's the kind you can't check on an app. You keep your pace slow and steady, because this is where your sleepy mind could get tangled if you sprint. So you take each mechanism and hold it up to the observations you've already felt. Frequent flickers, occasional stronger flares, hints of structure. Hotspots are attractive because they can create quasi-repeating patterns, but they require that a coherent blob survives long enough to orbit a few times without being shredded by shear and turbulence. That might happen, or it might not. Reconnection is attractive because it naturally produces sudden bursts and can happen repeatedly in a turbulent field. Turbulence and shocks are attractive because honestly, the environment is clearly turbulent, and outflows are attractive because they can explain why Sagittarius A stays dim overall. Energy may be going into motion rather than radiation. So which is it? This is where your open scholarly debate phrase arrives, soft and non-committal, the way you like it at bedtime. Historians still argue whether the story of black hole flare research is best told as a march toward one correct mechanism, or as an ongoing acceptance that multiple mechanisms can operate at once, because nature rarely picks a single clean narrative when it can run an ensemble cast. In the Sagittarius A star case, researchers debate how to disentangle overlapping processes when the data are rich, but the environment is brutally complex. You let that ensemble cast idea settle. It's calming. It means you don't have to force a single answer tonight. You can simply understand the palette of possibilities. Now you drift a little closer to the inner region in your imagination. You picture the event horizon not as a hard surface, but as a boundary of no return, and you picture the emitting region as a zone just outside it, plasma swirling, heating, cooling, sometimes brightening. You remember that fast variability suggests small size, which suggests closeness to the black hole. Close in, orbital speeds become enormous, and relativity starts seasoning the light. Brightness can be boosted by motion toward you and diminished by motion away. Time itself behaves differently, which is creepy in an unbothersome way when you're half asleep. Joke 3, gentle. Near Sagittarius A star, even the photons look like they're late for something. And this is the part where Webb's shock becomes more than wow, it flared. It becomes wow, it's doing this often, and the patterns might let us diagnose the physical engine. Because if you can match flare shapes and timescales to cooling processes, how electrons lose energy, how magnetic fields change, you can start discriminating among mechanisms. But you don't do the discrimination yet. You let the question breathe. Because the next step, the one you're gliding toward, is the really juicy clue Webb offers. Not just that the light changes, but that different infrared wavelengths can change at slightly different times, like the flare is telling a multi-part story in slow motion. So you keep floating forward, still listening to the crackle of magnetic knots and the hush of orbiting hotspots, and you wait for the next riddle to reveal itself. You keep your attention on the flare behavior, letting it wash over you like distant thunder you're trying to time with your breathing. The sparks are still there, brighten, fade, brighten again. But now you notice something subtler, the kind of subtlety that only shows up when your instrument is quiet enough and your stare is steady enough. The light doesn't change the same way at every infrared colour. It's like listening to a chord instead of a single note. One tone swells first, another follows, and suddenly you're not just hearing that something happened, you're hearing the order in which it happened. In the data, this can show up as a time lag. A flare appears stronger or earlier in one infrared band, then later in another. It's not a huge delay. Often it's minutes, not hours. But minutes matter when the emitting region is tiny and close to the black hole. Minutes mean you're watching energetic particles cool down, change their radiation behavior, or move through different physical conditions. Minutes mean the flare has an internal storyline, and you, second-person traveller, are now watching the plot unfold in slow motion. You picture a burst of energetic electrons, fast, newly accelerated, suddenly produced near Sagittarius A star. At first, they radiate strongly at shorter infrared wavelengths, where higher energy particles tend to contribute more. Then, as they cool, losing energy through radiation and interactions, the emission shifts, becoming more prominent at longer wavelengths. So the redder infrared light might peak later than the bluer infrared light, or the reverse, depending on the exact process. Either way, a lag is like a fingerprint. It tells you about particle energies, magnetic fields, densities, and how the emitting blob evolves. Mainstream historical fact, laid down gently like a stepping stone, spectroscopy, splitting light into its component wavelengths, has been a cornerstone of astronomy since the 19th century, when scientists like Kirchhoff and Bunsen linked spectral lines to chemical elements. That historical leap is the reason modern astronomers can treat light not just as brightness, but as information about physics, temperature, composition, motion, energy distributions. Time lags between wavelengths are a modern twist on that same tradition. You're still reading light as a diagnostic, but now you're reading it in time as well as colour. You let that settle. The whole enterprise is quietly beautiful. You can't touch the black hole, you can't taste the plasma, you can't smell the magnetic field, but you can watch how the universe's glow changes from one infrared shade to another, and from that you can infer the hidden machinery. Now you move closer to the riddle feeling, because when different wavelengths peak at different times, there are multiple ways to interpret it, and each interpretation tells a different story about what the flare is. One possibility, synchrotron cooling. Electrons spiraling in magnetic fields emit synchrotron radiation. Higher energy electrons cool faster, so emission at shorter wavelengths can rise and fall earlier, while longer wavelengths linger. Another possibility, expanding blob models, where a clump of plasma expands after being heated, changing its optical thickness and shifting the peak emission to longer wavelengths over time. Another possibility, the flare isn't one blob at all but a sequence. One region triggers another, like a chain reaction moving through the inner flow. You keep the cadence calm, because even though these are complicated ideas, you don't need to do math to feel the logic. A time lag means evolution. Evolution means physics in motion. Joke 1. Quiet. The black hole is basically sending you a delayed text, flare now, explanation later. And scientists are left staring at their phones going, what did you mean by this? You imagine how frustrating and thrilling this is for researchers. On one hand, the lag is exactly what you want, a clue with structure. On the other hand, the lag is also exactly what you don't want, a clue that forces you to pick between models that can mimic each other if you squint hard enough. This is where your open, scholarly debate phrase slips in, perfectly at home in the uncertainty. Historians still argue whether the most important breakthroughs come from a single, decisive observation, or from the slow accumulation of many ambiguous ones that gradually corner the truth. Time lag studies sit in that second category, rich, suggestive, but rarely case closed on their own. They push theories to sharpen, to predict specific lag patterns, and to risk being wrong. Now your quirky or fringe tidbit arrives, like a strange little souvenir you find in the gift shop of serious science. There's a persistent allure, especially in pop science corners, of treating any time lag or quasi-rhythm near Sagittarius A star as if it might be a message or a signal. Not necessarily aliens, though someone always tries, but a kind of cosmic Morse code. The mainstream view is much more grounded. Lags are physical delays from cooling, propagation, or geometry. Still, the fact that the galactic center can produce structured timing makes it irresistible to people who want the universe to be talking to them, not merely behaving. And honestly, even sober scientists can feel the temptation. The data can look eerily intentional when you forget it's plasma being dramatic. Joke 2. If the universe ever did want to send a message, it would absolutely choose a format that requires a decade of analysis, 3 committees, and a graduate student quietly aging into dust. You keep your focus on what Webb can do with these lags, because Webb isn't just sensitive, it's stable enough to track changes cleanly and separate genuine astrophysical variability from instrument wobble. That matters. A false lag is the kind of mistake that haunts you, but a robust lag repeated across events becomes a lever you can use to pry open the physics. You picture scientists comparing flare events. Does the lag scale with flare brightness? Does it appear only in stronger flares? Is it consistent from event to event, or does it vary, suggesting multiple mechanisms? Do the shorter wavelengths always lead, or do some flares reverse the order? Each answer nudges you toward a picture of the emission region, how compact it is, how magnetized it is, how quickly particles are accelerated and then cooled. And while you're drifting in this slow, sleepy way, you start to feel the environment as layered. Perhaps the shortest wavelength emission comes from very close in, hotter, more energetic, more compact, while longer wavelength emission arises from slightly farther out or from later stages of the same event. The flare is like a stone dropped into water, a sharp splash, then widening ripples. Different wavelengths trace different ripples. You let yourself remember the earlier suspects from Section 9, hotspots, reconnection, turbulence, and you realise time lags are one of the best tools for discriminating among them. Reconnection could accelerate particles quickly, producing a sharp early peak. Expansion models could naturally produce delayed, longer wavelength peaks. Orbiting hotspots could produce repeated modulations, but may or may not produce consistent lags depending on the cooling times. Turbulence might produce a more smeared and variable lag behaviour, and your mind, drowsy but engaged, can hold the tension. Webb has given you a new kind of evidence that is both clarifying and complicating. It's like turning on a dimmer switch in a dark room. The shapes become visible, but now you can also see the clutter, and you have to decide what matters. Joke 3, soft as a sigh. Congratulations, you have upgraded from mystery blob to mystery blob with timing problems. As you keep gliding forward, you sense the next step waiting like a doorway. Once you accept that the flare has timing structure, you have to ask what that timing says about the geometry of the accretion flow itself. Is there a thin disk? A puffed up lopsided torus? A hot radiatively inefficient flow? Something that doesn't match the classic textbook picture? The time lag riddle is nudging you toward the larger question, not just why does it flare, but what shape is the whole feeding system, and how does that shape make Sagittarius A star quiet in brightness but loud in behaviour? You keep watching the delays, the staggered peaks, the gentle echoes in light, like a lullaby sung in rounds, until your mind is ready to step into the next part of the story. You keep watching those staggered flare peaks in your mind, the way one infrared shade swells first, then another follows, and you realise the flares aren't just telling you that particles get energised and cool. They're also whispering something about shape, about geometry, about how matter arranges itself when it tries to fall into a gravitational pit that doesn't offer handrails. Because the old comforting picture, matter forms a nice thin pancake-like accretion disk and spirals neatly inward, is one of those textbook scenes that works great on a whiteboard, and less great inside the Milky Way's crowded, turbulent centre. Sagittarius. A star has always been awkward for the classic disk story. It's too dim for the amount of gas theoretically available. It flares too often for something supposedly stable, and Webb's steady stare is making that awkwardness feel less like an exception and more like the point. So you take a slow step into the question. Is there even a proper disk here? You picture the classic disk anyway, because your brain likes pictures. A thin disk is cool and orderly. Gas settles into a plane, friction heats it, it glows, it spirals inward. It's the kind of structure that can shine brilliantly, like in quasars, where the central black hole is actively feeding, and the disk is radiating like a cosmic furnace. But Sagittarius A star isn't radiating like that. It's not bright the way a thin, efficient disk tends to be. It's more like a black hole on a diet, with the occasional snack that somehow still manages to cause a small commotion. And that pushes you toward newer, messier models. Models that sound less like disk and more like hot, puffy, chaotic flow. In those models, the gas doesn't settle neatly. It stays thick, turbulent, magnetized. It's so hot and tenuous that it can't radiate its energy away efficiently. Instead of shining that energy as light, it keeps the energy in the particles and fields, and a lot of material may get blown back out in winds before it ever reaches the event horizon. You can feel why this might fit the Webb story. A hot, thick flow can be dim overall while still being restless on small scales. It can flicker and flare as magnetic fields tangle and snap, as little blobs heat up and cool, as the inner region rearranges itself like a half-awake sleeper. Here's your mainstream historical fact, placed gently like a familiar book on a nightstand. In the 1970s, astronomers found that many galaxies host extremely bright central engines, active galactic nuclei, powered by accretion onto supermassive black holes. That's when the accretion disk as power plant idea became central to how we explain quasar brightness. Sagittarius A star matters because it's a nearby counterexample. A supermassive black hole that exists without the quasar-level blaze, forcing you to ask what changes when the feeding rate is low and the environment is messy. Now you linger in the maybe not disk notion, because it's both unsettling and soothing. Unsettling because it means your tidy mental picture is wrong. Soothing because it explains the constant subtle activity. If the flow is inherently turbulent and magnetically dominated, flickering is normal. The flares aren't interruptions, they're the system breathing. You imagine the inner region as a thick glowing donut of plasma, except donut makes it sound stable, and this is more like a donut made of smoke and electricity. It's puffy, lopsided, constantly changing. Matter swirls in, but a lot of it swirls out too. The black hole isn't a drain, it's a complicated junction where inflow and outflow negotiate. Joke 1, soft and sleepy. If you were expecting a neat spiral into doom, Sagittarius A star is more like a roundabout where half the cars panic and take the exit, and then your mind returns to the time lags. In a thin disk you might expect certain smooth, predictable temperature gradients. In a hot, thick flow you expect patchiness, localized heating events, expanding blobs, variable optical depths. The lag behavior Webb hints at starts to feel like it belongs to a messy, evolving structure rather than a clean, stable disk. This is where you let the open, scholarly debate phrase drift in, as promised, and you let it stay unresolved like a lullaby question. Historians still argue whether the history of accretion theory is best described as a steady refinement of one basic disk idea, or as a series of paradigm shifts driven by inconvenient objects like Sagittarius A star that force theorists to invent entirely new flow regimes. Even now, researchers debate which model family best captures the Milky Way's centre. Variations of radiatively inefficient flows, magnetically arrested scenarios, hybrid disk plus corona pictures, or something that changes state depending on how much material arrives. Now for your quirky tidbit, something a little offbeat but still tethered to real scientific culture. Some researchers, half joking and half serious, talk about the accretion flow near a low-luminosity black hole as being all atmosphere, no ground, meaning you have a hot, tenuous, magnetized region, more like a corona than a thick, shining disk, and the idea of a crisp surface, or even a crisp disk plane, becomes fuzzy. It's an oddly poetic framing, and it matches what your sleepy brain can picture. A stormy halo of plasma, rather than a neat ring of glowing pancakes. Joke 2, turns out the disk might be more like a cosmic souffle. Looks structured until you breathe on it. You continue, and the narrative glides into a practical consequence. If Sagittarius A star lacks a classic thin disk, then it makes sense that it's dim. In radiatively inefficient models, the gas can be so hot that ions carry most of the energy while electrons, the ones that radiate efficiently, don't get enough of that energy to shine brightly. Or the flow becomes so magnetized and turbulent that energy is redirected into outflows rather than light. Either way, the black hole stays modest in luminosity while still being physically busy. And busy is exactly what Webb is picking up. You imagine the flare events as local reorganizations in this puffy flow. A knot of magnetic field lines tightens, reconnection releases energy, electrons get accelerated, they radiate in near-infrared, they cool, the emission shifts, maybe the blob expands, producing the lags you noticed. The flare is a small story inside the larger story of a system that can't settle down. You keep your pace slow, almost whispery now, because this is concept heavy and you don't want to jolt the listener awake. You repeat the key feeling in different textures. Not a flat disc, but a thick swirl. Not steady, but twitchy. Not bright, but alive. Joke 3, gentle, Sagittarius. A star is the kind of quiet that still somehow generates a weekly incident report. And as you float onward, you realise that Webb's shock isn't just we saw flares, it's the flares make the old picture feel inadequate. The data pushes you to accept a feeding system that's more like weather than plumbing, more like a simmering magnetised fog than a neat spiral staircase into darkness. You hold on to that new mental image, this puffy, lopsided, radiatively inefficient flow, because it becomes the bridge to the next thought. If you can't always see a disk, can you still see the black hole in some other way? Not with an image of the event horizon, but with timing, with spectra, with the kind of indirect evidence that feels like hearing someone move in the next room. You keep drifting forward, letting the idea of a non-classic disk settle over you like a warm blanket, and you prepare to compare what Webb does well with what other instruments do, because black holes are the kind of objects that require a whole orchestra of methods just to be understood at all. You keep that image in your mind, the accretion flow not as a tidy pancake, but as a puffy, magnetised fog, and you feel the story wanting to do something very human. It wants to demand a picture. It wants a clean, iconic shot, the kind you can put on a poster and point at dramatically while saying, "That's the black hole, right there." Because your brain loves pictures. Your brain loves closure. Your brain would like the universe to stop being abstract and start being cooperative. But Sagittarius A star doesn't do cooperative. So you drift into a quieter truth. Seeing a black hole is not always about a photograph. Sometimes it's about a shadow. Sometimes it's about timing. Sometimes it's about spectral fingerprints. Sometimes it's about inference so careful it becomes its own kind of vision. And this is where you naturally compare Webb to another famous set of eyes, the Event Horizon Telescope, the global network of radio dishes that achieved the kind of black hole imagery people once swore would be impossible. The EHT's method is different, very different. It doesn't look in infrared, it looks in radio wavelengths, using the trick of combining telescopes across Earth to act like one enormous virtual dish. It's like turning the planet into a camera lens. Very poetic, very inconvenient for anyone who hates scheduling. Mainstream historical fact gently placed. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, M87 star, the supermassive black hole in galaxy Messier 87. That image was not a photo in the everyday sense. It was a reconstruction based on radio interferometry data, and yet it revealed a bright ring-like structure around a dark central region consistent with the black hole shadow. It was a milestone in astronomy, and it also quietly taught you something important. Black holes can be seen through the behaviour of surrounding light, not by imaging the hole itself. Now you might wonder, sleepy, curious, slightly sarcastic, why not just do that for Sagittarius A star and call it a night? And the answer is, they did. The EHT later produced an image for Sagittarius A star as well, but it's harder, because Sagittarius A star is smaller in apparent size and more variable on short timescales. It changes while you're trying to take the picture. Imagine trying to photograph a candle flame in a windy room using a camera made of continents. That's the vibe. Joke 1. Soft Sagittarius. A star is basically the subject who insists on blinking in every group photo and then acts offended when you ask for just one more take. Here's the quiet beauty. Webb and EHT aren't rivals, they're complementary. Webb can't resolve the event horizon scale shadow directly in the same way. Its resolution and wavelength regime are different. But Webb can observe infrared variability, time lags, spectra, and the thermal glow of dust and stars in the region. EHT can probe the radio emission on horizon scales, sensitive to different particle populations and magnetic field structures. Together they're like two senses describing the same creature, one hearing its breathing, the other tracing its silhouette. You stay in second person, feeling yourself stand between these instruments as if you were in a control room with multiple monitors. On one screen, you have Webb's light curves, the flickers and flares, those tiny, frequent changes that made scientists swallow hard. On another screen, You imagine the EHT's reconstructed ring-like structures and shadows, not as static photos, but as averages over turbulent behaviour. Both are true, both are incomplete, both are powerful, and this leads you into the central idea of this section. A black hole can cast a shadow without being seen, in the way your eyes see a cat on the couch. It's a gravitational lensing effect. Light from hot plasma around the black hole gets bent. Some paths are captured, some wrap around and reach you, creating a bright ring and a dark central depression. The shadow is the region where light is swallowed or redirected away. It's geometry. It's space-time doing a trick with beams. Yet Webb's work is more intimate and more temporal. Webb watches the glow change, and those changes can tell you about orbits and cooling and reconnection. Webb sees the black hole's neighbourhood behave, like watching ripples and guessing the shape of the stone beneath. Now for your quirky tidbit, slightly fringe in flavour, but grounded in the psychology of science. There's a long tradition of people insisting that an indirect measurement is less real than a picture, as if reality only counts when it looks like a postcard. Astronomers have always fought this misunderstanding. Neptune was real before it was visually confirmed. Exoplanets were real when they were first detected by the wobble of a star. Gravitational waves were real as a concept long before the first detection. Black holes too were real for many scientists from dynamical evidence long before any shadow image existed. The fringe part is the stubborn human belief that only the eye can certify truth, an idea that science keeps gently humiliating. Joke 2. If the universe had a customer service desk, it would absolutely say, "Your request for a simple picture has been denied. Please enjoy this graph instead." And here comes your open scholarly debate phrase, calm and unresolved. Historians still argue whether iconic images like black hole shadows change science itself, by guiding funding, public interest, and even the questions researchers prioritise, or whether they mostly change the story of science, while the underlying progress would have happened anyway through papers, models, and incremental improvements. In other words, does the picture drive the physics, or does the physics simply earn the picture after the fact? You let that debate drift by like a cloud, because tonight you don't need to choose. Tonight you just need to feel the continuum. Seeing. Sagittarius. A star can mean a shadow in radio, or a flicker in infrared, or the orbital dance of stars, or the spectral shape of emission, or the time lag between bands. It's a whole sensory toolkit built for an object that refuses to be direct. You return to Webb's strengths. Webb can measure how the infrared light changes, how it correlates across wavelengths, and how often flares occur. Webb can also help characterise the broader environment, dust structures, star clusters, gas streamers, providing context the EHT doesn't care about because the EHT is zoomed in like a person staring at one pore on a face. Webb sees the neighbourhood, EHT sees the edge. And this is why the shadow without a picture line matters. Even if Webb never produces a poster-ready event horizon shot, Webb can still tell you the black hole is active, the environment is dynamic, and the flow geometry is likely thick and turbulent. Webb can help you understand why Sagittarius A star looks the way it does to the EHT, because the EHT image is a snapshot of a system whose behaviour Webb is timing in exquisite detail. Joke 3. Gentle as a yawn. Sagittarius. A star is the kind of celebrity who gives one blurry paparazzi photo and then releases 1,000 cryptic tweets. Webb is reading the tweets, and now, as you glide forward, you feel the next question forming. If seeing is really a collection of indirect senses, then what else in the neighbourhood might be shaping what you see? Not just the black hole and its hot flow, but the stars around it, their winds, their outbursts, their constant shedding of material that can both feed and disrupt the central engine. So you keep moving, still listening for the next quiet clue, still letting the story flow like slow, warm air from a fan in the dark. You keep floating forward with Webb's quiet multi-tool vision in your pocket, Light curves on one side, shadow imagery on the other, and now the story naturally widens to the neighbourhood itself. Because a black hole does not live alone. It lives in a loud apartment building where the neighbours are massive stars that never stop vacuuming at 2 a.m. You're still aimed at the galactic centre, still present tense, still second person, and now you can almost feel the crowding. Stars packed so tightly that the sky looks busy even when it's still. And these aren't gentle, long-lived stars like the sun, content to glow politely for billions of years. Many of the bright ones near Sagittarius A are big, hot and impatient, short-lived giants that dump material into space through relentless winds. Those winds matter, a lot, because for Sagittarius A, the food supply is not a neat stream. It's more like windblown dust and drizzle, stirred by stellar tantrums. You remember the idea from earlier. The black hole is underfed, but not because the pantry is empty. It's underfed because the pantry is chaotic and the ingredients keep flying past the bowl. You drift closer to the central cluster and imagine winds as invisible rivers flowing outward from stars, colliding with other winds, compressing gas, creating shocks, heating pockets of plasma. In this environment, the material that eventually spirals towards Sagittarius A isn't just gas, it's gas with history. Gas that's been blasted, stirred, ionized and shaped by the personalities of nearby stars. Mainstream historical fact, steady and simple. In 2006, the Nobel Prize in Physics went to John Mather and George Smoot for work on the cosmic microwave background. A reminder that modern astronomy is often about extracting faint signals from overwhelming noise, measuring tiny differences to infer huge truths. That same mindset applies here. The signal of Sagittarius A's accretion behaviour is embedded in the noise of stellar winds and crowded emission sources. You don't get a clean laboratory, you get a messy sky, and you learn to measure anyway. Now you let the neighbourhood become vivid. You picture a few especially influential residents, massive luminous stars that shed strong winds and, importantly, Wolf-Rayet stars, which are basically stars in a late intense phase of evolution, losing mass at dramatic rates. Their winds are fast and dense, and when many such stars sit near the black hole, their outflows can collectively feed a hot ambient medium. That medium can provide the raw material for accretion, even if only a small fraction actually makes it inward. But feed is only half the story, because winds can also prevent feeding. If winds create enough pressure and turbulence, they can keep gas from settling into a stable inflow. They can stir the inner region so thoroughly that angular momentum never gets bled off efficiently. They can shock heat material so it becomes buoyant and escapes rather than sinks. In some models, Sagittarius A's dimness is partly because so much of the available gas is blown away or kept hot and puffy, always swirling, rarely committing. You feel the irony, and it's soothing in a dark humour kind of way. The black hole sits at the centre, like the ultimate gravitational landlord, but the tenants keep leaving their doors open and blasting fans so nothing ever settles. Joke 1, gently. Sagittarius. A star is surrounded by stars that basically run industrial leaf blowers 24/7, and then everyone acts surprised the place is messy. Now you remember Webb again. Webb's infrared sensitivity doesn't just catch flare flickers, it can also help characterize the stellar population and dusty structures that set the boundary conditions for the whole system. And that matters because when you interpret a flare, when you argue hotspot versus reconnection, you need to know what the environment is doing. A flare might be triggered by a local magnetic event, sure, but the fuel and field geometry are shaped by winds and interactions in the surrounding cluster. This is also where multi-wavelength coordination becomes essential, even if you're not calling it that out loud. Infrared flares sometimes have counterparts in X-rays. Radio emission may respond on different timescales. The environment's thermal properties show up differently depending on wavelength. Webb is one ear, other observatories are other ears. Together they make the sound less ambiguous. Now comes your quirky tidbit, slightly odd, a little fringe-flavoured, but anchored in the real weirdness of the region. For years, astronomers watched a gas cloud nicknamed G2 Swing close to Sagittarius A star and debated what it actually was, a simple gas cloud or a star wrapped in gas and dust, or something in between. The reason it became such a big deal is that it was a rare chance to watch fresh material pass near the black hole and see whether the black hole would noticeably brighten afterward, like a sleeping animal smelling food. The results were complicated. Not the dramatic feast some headlines wanted, but not nothing either. More like a reminder that feeding is inefficient and the neighbourhood doesn't hand over matter without a fight. Joke 2, people expected a black hole buffet, and Sagittarius A star basically said, "Thanks, I'll nibble later," and went back to flickering. This brings you to the deeper, open question. How much of Sagittarius A star's variability is driven internally, magnetic reconnection, turbulence, and how much is driven externally, changes in the supply of gas from winds and passing clumps? And here you slide in the required open scholarly debate phrase, soft as a pillow. Historians still argue whether the best way to understand systems like Sagittarius A star is bottom-up, starting from plasma microphysics and building upward, or top-down, starting from the galactic environment and working inward, because each approach can explain some features while leaving others stubbornly unresolved. In practice, researchers argue about where the dominant control knob is, the inner magnetic turbulence, or the outer feeding conditions. You let that argument remain unresolved, because your job tonight is not to win the debate, it's to make the debate feel like a slow tide you can listen to. You imagine the winds again, colliding and making shocks. Shocks are important because shocks can accelerate particles, another flare pathway. If a shock front passes through a region near the black hole, it can temporarily boost emission. It can also seed turbulence, creating the tangled magnetic environment reconnection loves. And there's another quiet twist. Massive stars don't just blow steady winds. Many vary, pulsate, or interact in binaries. Colliding wind binaries can produce their own energetic phenomena, complicating the background. In a crowded region, separating black hole flare from stellar mischief can be tricky. That's part of why the Webb monitoring is so valuable. Timing and spectral behaviour can help distinguish sources. Sagittarius. A star's immediate environment has a characteristic variability signature that differs from ordinary stellar flicker, usually is doing a lot of work there. Joke 3, soft. The galactic centre is basically an astronomical group chat where everyone is typing at once, and you're trying to figure out who sent the one message that matters. You keep your narrative gliding forward, and you feel the next step approaching. If the neighbourhood can both feed and disrupt the black hole, then the flares Webb sees might be the inner region's response to a constantly changing wind-stirred supply line. That points toward methods that can map the inner region indirectly, turning flickers into distances, delays into structure. Which means you're about to use light itself like sonar, like cave mapping clicks in the dark, and you, half asleep and steady, continue onward. You keep gliding forward from the noisy apartment building neighbourhood of stellar winds, and you let your mind do something clever and quiet. Instead of trying to see the black hole's immediate surroundings directly, you start using light as a probe, not just as a picture, but as a way to measure distances you can't reach. Because when Sagittarius A star flickers, that flicker doesn't just vanish into the void. Some of that changing light can bounce, metaphorically, off surrounding material. It can be absorbed and re-emitted. It can heat dust, which then glows back a moment later. It can light up different regions with slight delays, like a flashlight sweeping across fog. And those delays, those faint echoes, are the universe's way of handing you a tape measure. You are in this second-person drift using something like reverberation mapping, a technique that sounds like it belongs to acoustic engineers, but in astronomy it's a way of turning timing into geometry. A flare happens near the centre. Nearby material responds after a delay. The delay tells you how far away that responding material is, because light has a speed limit and it actually obeys it, unlike your brain at 2 a.m. when it decides to sprint through every memory you've ever had. Mainstream historical fact placed gently and clearly. Astronomers have used reverberation mapping for decades to estimate the sizes of emitting regions around active galactic nuclei, especially to probe broadline regions where gas responds to variations in the central source. The technique became a major tool in the late 20th century because it lets scientists measure scales far too small to resolve directly with imaging. It's a classic example of astronomy's favourite move. When you can't take a picture, you take a time series and let physics do the geometry for you. So you imagine Sagittarius A star's flare as a kind of cosmic clap. Not a loud one, more like a soft snap of fingers in a vast carpeted room. The snap happens close in, near the black hole's inner flow. Then, a moment later, you might see a slightly delayed response in a different wavelength band, or a subtle brightening in surrounding dust, or a change in emission that suggests the flare's energy has propagated outward. You're not literally hearing an echo, but you're watching an echo in light. And this is where Webb's steadiness becomes almost spooky, because Webb can monitor in infrared with the kind of sensitivity that makes these small delays feel reachable. The flickers you've been tracking, especially when you compare different wavelengths, start acting like a sonar ping, a ping that helps outline the cave you're in, even though you can't turn on the overhead lights. Joke 1, soft. You're basically using the galaxy's most dangerous object as a flashlight, which feels like letting a volcano hold a candle for you. Now you slow down and savour what this cave mapping might tell you. If the flare is produced by energetic electrons spiralling in magnetic fields, the emission at one wavelength might be direct synchrotron radiation. Meanwhile, dust farther out could be warmed slightly and re-radiate in longer infrared later. Or an expanding blob could become optically thin at different wavelengths at different times, producing apparent echoes that are really just the flare evolving as it grows and cools. Either way, the timing structure becomes a physical constraint. It tells you how quickly energy moves, where the emitting regions likely sit, and how large the system's active zone is. You also keep in mind the messy neighbourhood from last section. Stellar winds and dense clumps of gas mean there's plenty of material for flare light to interact with. Some regions might respond quickly, others slowly, depending on density and composition. This isn't a clean lab. It's an environment where the echo pattern can be complicated, like shouting into a cave full of side tunnels and trying to map it from the returning sound. Joke 2. Sagittarius. A star gives you an echo, and the universe says, "Cool, now solve the cave." Now your open, scholarly debate phrase drifts in, unhurried. Historians still argue whether reverberation techniques are best thought of as direct measurement, or model-dependent inference, because the timing delays are real, but the interpretation depends on assumptions about geometry, inclination, and how different materials respond to irradiation. The debate isn't about whether the method works. It does, but about how confidently you can translate a delay into a detailed 3D picture when the environment is turbulent and the responding material may be clumpy. And yes, clumpy matters. A smooth ring of dust would produce clean, predictable echo-patterns. A clumpy, uneven distribution produces messy echoes, with some regions lighting up more than others. Sagittarius A star's neighbourhood, as you've already felt, is basically clump central. Now for your quirky tidbit, the kind that makes you smile without waking up. There's an old, half-joking tradition among astronomers of calling certain echo-like behaviours light echoes, and the phrase is so vivid that it sometimes tempts people to imagine literal mirrors in space. In reality, it's usually scattering off dust or delayed re-emission, but the romance of echoes sticks because it captures the eerie experience of watching the past arrive late. A flare happens, and then, minutes or longer later, you see the environment respond, like the universe is replaying the moment from a different angle. That idea can feel almost philosophical at night. You're always seeing delayed light anyway. But echoes make the delay structured. and structure is what your mind loves. You keep moving through the idea that Webb's flare monitoring isn't just black hole drama, it's also a mapping tool. If the flare happens near the innermost flow, and if a delayed response suggests material at some radius, you can start to sketch a rough layout: inner hot plasma, outer dust, streamers, maybe even the boundaries where stellar winds dominate. You're turning timing into architecture. And you remember the time lag riddle from section 10. Different infrared bands peak at different times. That can be intrinsic flare evolution, but it can also be interpreted as a kind of internal echo, where different zones respond on different timescales. The flare might begin in the tightest region, then propagate outward, heating or accelerating new particles farther out, shifting the emission. Like a ripple moving through a pond, but the pond is magnetized plasma in curved space-time. Joke 3. Soft as a blanket settling. It's the only pond where the ripples might try to orbit you back. You keep your tone low and your pacing slow, and you don't pretend the map is perfect. You acknowledge the honest truth. Astronomers build competing models, and each model can produce slightly different echo patterns. Some models emphasize expanding blobs, some emphasize localized reconnection events, some emphasize orbiting hotspots that brighten and dim with relativistic beaming. Reverberation-style thinking becomes the way to check. If the model predicts one lag pattern and Webb observes another, the model has to flinch. So you're watching a method in action. Flickers are no longer just surprises, they're measurements. And now, because your outline promises it, you let this section's final feeling be that you have found a way to see in 3 dimensions without ever resolving a clear image. You're using time as depth. You're using delay as distance. You're using the black hole's own restless behavior as a lantern to outline its immediate surroundings. You keep drifting forward because the next step is almost inevitable. Once you can map and time and infer, the mind starts wondering about the weird possibilities, about hidden companions, clumpy debris, odd orbital structures, those fringe-flavoured ideas you can entertain with one eyebrow raised, even as you keep your feet planted in the data. You keep floating forward from the idea of light echoes and cave mapping, and now your mind does that late-night thing where it opens a door labelled "What If" and peeks inside with one eye half closed. You're not doing this because you want to replace good evidence with spooky speculation. You're doing it because, in a region as crowded and turbulent as the galactic centre, it's genuinely reasonable to ask whether the flare patterns Webb sees could be influenced by something additional, something not obvious in the standard picture. So you let yourself entertain hidden companions and clumpy debris with the right attitude, curious, careful, and mildly skeptical, like you're reading a conspiracy thread, but you're also a scientist with a mug that says, "Show me the data." You start with the simplest hidden companion idea. Maybe there's an unseen object, another black hole, a neutron star, a dense star remnant, moving through the inner region, perturbing the flow. Not perturbing in a Hollywood way, like 2 black holes playing billiards. More like a heavy object stirring the soup as it passes. In such a dense environment, this isn't fantasy. Stellar remnants should exist in large numbers. Some could drift inward over time through gravitational interactions, building a kind of invisible crowd around the central giant. And if a remnant passes through gas or interacts with magnetic structures, it might help trigger local disturbances, compression, shocks, reconnection, nudging the flare rate or flare shapes. Not creating the physics from scratch, but tapping the system's shoulder. Mainstream historical fact laid down gently. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, and its orbital decay matched the energy loss predicted by gravitational waves, an early crucial confirmation of relativity's deeper implications. The reason this matters here is not because Webb is detecting gravitational waves, but because it reminds you that hidden companions are a normal part of astrophysics. You can infer unseen objects from timing, motion, and subtle dynamical effects long before you ever see them directly. The universe is full of things that only reveal themselves indirectly. Now you let the idea expand. Some researchers talk about the possibility of a dense cluster, or cusp, of stellar mass black holes and neutron stars near the galactic center. If that's true, the inner environment is not just a black hole plus gas. It's a black hole plus gas plus a swarm of invisible weights. That swarm could contribute to gravitational potential, alter gas dynamics, and in rare cases even produce its own transient signals. But you keep your skepticism switched on. Most of the flare behavior Webb sees can be explained by processes in the accretion flow itself: turbulence, reconnection, orbiting hotspots. A hidden object is not required. It's just a possible complication, a seasoning the universe might have added. Joke 1 softly. The galactic center is already complicated and your brain is still like, but what if there's also a secret roommate? Then you move to clumpy debris. The galactic center is full of streams and filaments. It's full of gas that can fragment into denser knots. In a chaotic flow, you can get transient clumps, little over-densities that move inward, get stretched, heated, and possibly flare as they interact with the inner magnetic environment. If accretion is episodic, snack, pause, snack, then the flares could track those snacks. Not always, not neatly, but sometimes. You picture a clump drifting inward like a leaf caught in a whirlpool. As it approaches the inner region, tidal forces stretch it. Heating increases, magnetic fields grab at its charged particles. Maybe it triggers reconnection, maybe it shocks, maybe it just adds a little extra mass at the wrong moment, and the system responds with a brighter flare. And because you're in second person, you feel the temptation to imagine a thing you can point at. A blob, a culprit, a named object. Humans adore named objects. It feels cleaner than admitting the culprit might be the entire flow being chaotic. Joke 2. If flares were a crime scene, you desperately want a suspect with a face, but the suspect is mostly plasma vibes. Now comes your open, scholarly debate phrase, and it fits here perfectly because this is where interpretation fights begin. Historians still argue whether scientific communities are too quick to dismiss exotic explanations when standard models can be stretched to fit, or too quick to entertain exotic explanations when standard models already fit well enough. Around Sagittarius, a star, the debate takes a practical form. Do you need extra companions or special structures to explain variability? Or is the inner flow's turbulence and magnetism sufficient? The line between plausible complication and unnecessary ornament is where a lot of late-night seminars go to die. You keep that debate unresolved, like a lullaby with an unfinished rhyme. Now for your quirky tidbit, this one comes with a raised eyebrow. There have been occasional speculative musings that if a small object, say a compact remnant, passed through the inner accretion region on the right trajectory, it could create a repeating signature, a sort of transient stirring spoon that makes flares cluster in time. It's not the mainstream expectation, it's more like an idea that gets mentioned, tested, and usually set aside unless the data demand it. But the very fact it's discussable tells you something about the galactic center. It's so crowded and so extreme that unusual interactions are not impossible, just hard to confirm. You let that sink in. Hard to confirm is the theme of this whole story. The black hole doesn't hand you a clean diagram, it hands you flickers, delays, and probabilities. Now you bring your attention back to Webb's flare patterns. If there are hints of rhythm, those quasi-periodic features that made people count beats, one fringe-leaning possibility is that something is orbiting and modulating emission. A hotspot, yes, but perhaps also a longer-lived structure, like a standing shock or a persistent magnetic feature, or even the influence of an orbiting object shepherding plasma. Again, not required, but tempting. And your sleepy mind enjoys temptation, as long as it stays PG-13 and doesn't invite you to buy a weird supplement. Joke 3, gentle. The moment the data looks rhythmic, half the field reaches for orbiting hotspot, and the other half reaches for statistical artifact, and everyone forgets to drink water. You hold all these possibilities lightly, you don't marry any of them. You simply accept that the galactic center is a crowded stage with many actors, some visible, some inferred, and Webb has just given you a closer listen to the dialogue. And as you glide onward, you feel the story pivot from what might be hiding back to the human side of science. Because once the data arrives, the real turbulence begins. Interpretation, disagreement, pride, funding, and the slow, stubborn process of turning flickers into consensus. You keep drifting forward from that slightly mischievous, what if there's a secret roommate thought, and now you arrive at the most reliably chaotic region in the entire galaxy. Not the black hole's plasma, not the dust lanes, not the stellar winds. No, you arrive at the human circle around the data. Because once Webb shows you flickers and flares and suspicious hints of structure, the universe goes quiet again, and the noise comes from conference rooms, Slack threads, late-night emails, and the gentle, devastating phrase, "I'm not convinced." You're still in second person. You're still moving through the story like a slow walk. But now you're walking through the sociology of science, which is somehow both calmer and more emotionally explosive than a supermassive black hole. You picture the scene. A researcher pulls up Webb's light curve and the room leans in. Someone points at a flare and says, "That one is clean." Someone else says, "Define clean." A third person says, "Could it be an instrumental effect?" And everyone groans, because yes, it could always be an instrumental effect, and the universe would absolutely do that to you if it could. This is the first layer of the argument loop. Is the signal astrophysical or procedural? Webb is stable, yes, but every serious team assumes their instrument is guilty until proven innocent. Calibration, background subtraction, contamination from nearby stars in a crowded field. These are not boring footnotes. They are the difference between discovery and embarrassment. The higher the sensitivity, the more you can be tricked by tiny systematic errors, like buying a microphone so good it records your stomach grumbling, and then trying to decide if your house is haunted. Mainstream historical fact, steady and human. In 1912, Alfred Wegener proposed continental drift, and the idea was ridiculed for decades not because it was absurd, but because the mechanism and evidence weren't yet convincing to the broader community. It took time, additional data, and a workable physical explanation for the consensus to shift. The reason you carry that fact into this Webb story is simple. In science, the hardest part is often not noticing a pattern. It's getting everyone to agree it's real, and then agreeing on what it means. So you watch the modern version of that unfold. Some scientists see quasi-rhythmic behaviour and lean toward orbiting hotspots or coherent structures. Others see the same wiggles and say, "You're fitting your hopes." Some prioritise magnetic reconnection because it naturally explains bursts and frequency. Others argue for turbulent flow models because turbulence can mimic almost everything, given enough time and enough caffeine. And then there's the more subtle disagreement. Even if everyone agrees these are real flares, there's still the question of what counts as shocking. Is the shock that Sagittarius A star is more active than assumed? Or is it that Webb's time coverage reveals a baseline restlessness that earlier snapshots couldn't capture? The same data can feel like a surprise or an inevitability depending on which mental model you walked in with. Joke 1, light and sleepy. The universe gives you a flare, and humans respond by inventing 3 camps, 5 sub-camps, and 1 person who refuses to join anything because labels are limiting. Now you drift through the second layer of the argument loop, models versus meaning. Observations are one thing, interpretation is the long, slow wrestling match. If you propose a hotspot model, you have to specify how hotspots form, how long they survive, what their orbital radii imply, and whether the implied timescales match the black hole's mass and spin. If you propose reconnection, you have to explain field geometry, particle acceleration, and expected spectral evolution. If you propose expanding blobs, you have to justify the expansion speed, the optical depth evolution, and why the lags line up. It's not that any model is ridiculous. It's that the region is so complex that multiple models can reproduce similar-looking light curves with different assumptions. And scientists, being scientists, are allergic to assumptions that aren't tested. Now you slip in the quirky tidbit, the kind that's half cultural and half comically true. The argument loop in astrophysics often runs on a shared ritual, where someone shows a plot, someone asks about error bars, someone asks about selection effects, and someone in the back says, "Have you tried a completely different method?" That person is both the hero and the villain of the meeting. The hero because they might be right. The villain because they have just added 6 months of work to everyone's life. Joke 2. Every astronomical debate eventually includes the phrase, "just a quick reanalysis," which is the scientific equivalent of someone saying, "It'll only take 5 minutes," right before your entire evening disappears. Now you bring in your open, scholarly debate phrase, perfectly matched to this human swirl. Historians still argue whether scientific disagreements are best understood as healthy skepticism or as social dynamics, status, seniority, institutional momentum, wearing a lab coat. In the case of something like Webb's Sagittarius A star monitoring, you can see both. The skepticism is real. Crowded fields are hard, flares are complex, statistics are tricky. But the social layer is real too. People have invested years in particular models, and it's emotionally difficult to watch the universe prefer someone else's explanation. You keep this PG-13 and gentle, but honest. Science is not a single mind. It's a flock of minds trying to align. Then you drift into the third layer, funding and telescope time. Webb is precious. Everyone wants it. If you claim Sagittarius A star is doing something particularly interesting, you can justify more monitoring, more coordinated campaigns, more follow-up. That's not corruption. That's priority setting. But it does create incentives. Some teams emphasize how surprising the behavior is to make the case that it deserves more attention. Other teams push back, not because they're jealous. Well, not only because they're jealous, but because exaggeration damages credibility. Joke 3. Soft. Astronomers are the only people who can argue intensely about quiet behavior, while writing proposals that politely scream, "This is extremely important." You let that settle and you remember the content of the earlier sections, the flares, the time lags, the possibility of a puffy, radiatively inefficient flow, the influence of stellar winds, the light echo mapping idea. All those elements become chess pieces in the debate. Different groups arrange them into different stories. One story says, Sagittarius. A star is governed by magnetically driven turbulence. The flares are reconnection, and the time lags reflect synchrotron cooling and propagation in a hot flow. Another story says, the flares are orbiting hotspots near the innermost stable regions. Quasi-periodic hints might encode spin and geometry, and Webb's sensitivity finally makes that visible. A third story says, both are true in parts. The rhythm is weak and intermittent, and you should stop trying to make a single clock out of a storm. And hovering above all of it is the quiet, persistent work of people who refuse to argue until they've checked everything twice. They cross-correlate light curves, compare filters, simulate turbulent flows, test statistical significance, and coordinate with other wavelengths. They are the slow heartbeat of the field. They will never trend on social media, but they keep the story from turning into a fairy tale. You keep the narration gliding, no new intro, just a gentle forward movement toward what comes next. The question of how Sagittarius A star fits into the broader black hole family. Because once the arguments start, the only way out is more context. Compare it to other galaxies, other black holes, other accretion states. See whether our black hole is uniquely quirky, or just a normal black hole caught during a quiet but busy phase, and as you drift toward that bigger cosmic comparison, you can feel the human argument loop still spinning softly behind you, like a ceiling fan in a dark room, steady, murmuring, not threatening, just reminding you that the universe is hard and humans are even harder. You keep drifting forward from the human argument loop, those polite academic knife fights over models and meanings, and you let the scene widen, The way your eyes adjust when you step outside and realise the sky is bigger than the street you are arguing on. Because one of the cleanest ways to calm an argument is to change the comparison set. So you lift Sagittarius A star out of its local drama and place it on the long shelf of black holes everywhere. And instantly the shock starts to feel less like a one-off surprise and more like a clue about categories. You imagine a museum hallway of galactic cores. On one side you have the loud ones, active galactic nuclei that blaze so hard they outshine their host galaxies, powered by black holes feasting on steady streams of gas. These are the quasars, the cosmic floodlights, the objects that make the early universe look like it had a nightlife problem. Their accretion disks are efficient, bright, and, at least in the simplified telling, structured enough to radiate huge amounts of energy. On the other side, you have the quiet ones, low-luminosity black holes that barely glow, that seem to sip rather than gorge, that go about their gravitational business without much spectacle. Sagittarius. A star belongs here, at least if you judge by average brightness. But Webb's monitoring is whispering a more interesting classification. Maybe quiet doesn't mean inactive. Maybe it means active in a different mode. A mode where the system's energy comes out as turbulence, magnetic rearrangements, and intermittent flares rather than as a steady, brilliant disk. So you walk down the hallway and compare. In distant galaxies, you often don't get the luxury of resolving the central region with this kind of fine timing. You measure total brightness, maybe spectra, maybe rough variability. If a nucleus is dim, it can get labelled low activity, and the story moves on. But Sagittarius A star is close enough that you can watch it fidget. Webb makes the fidgeting obvious, and that makes you wonder, how many quiet galactic centres are actually doing this, constantly simmering, occasionally sparking, while you just haven't had the sensitivity or the patience to notice? Mainstream historical fact plays softly like a bookmark. The realization that quasars are extremely distant, extremely luminous objects powered by accretion onto supermassive black holes became widely accepted in the 1960s after their redshifts and energy outputs were understood. That historical turning point matters because it created a spectrum of black hole behaviour, active versus quiet, luminous versus dim, and modern work is still about figuring out what controls where a galaxy sits on that spectrum at any given time. Now your mind settles into the idea of states, like a black hole has moods. In X-ray binaries, stellar mass black holes feeding on companion stars, astronomers talk about accretion states, high/soft, low/hard, transitions, jets turning on and off. The physics scales up, and many researchers suspect supermassive black holes also have analogous regimes. Not identical, but rhyming. If that's true, then Sagittarius A star might be in a low accretion state where the flow is hot and radiatively inefficient, and variability is a natural byproduct. And Webb's flares become less unexpected fireworks, and more the normal crackle of this state. You picture it like this. In a bright quasar, the accretion flow is so dense and steady that it glows smoothly, like a well-fed furnace. In a low-luminosity system, the flow is tenuous, magnetized, and turbulent, like embers that flare when a gust of wind hits. Both are accretion. They just radiate differently. Joke 1, drowsy. Some black holes are fine dining, and Sagittarius A star is gas station snacks eaten over the sink. Still food, just emotionally complicated. This broader view also reframes the shock scientists feel. It's not simply that our black hole flares, it's that the flare statistics and timing structure give you a template for interpreting other low-luminosity galactic nuclei. If Webb shows that a dim black hole can be constantly variable, then variability becomes a key diagnostic across the universe. You can almost feel researchers taking Sagittarius A star's flicker patterns and asking, if we observe a similar pattern in another galaxy, faint, red, irregular, with occasional bursts, does that imply similar magnetic turbulence, similar radiatively inefficient flow, similar outflows. The local specimen becomes a calibration point, a Rosetta Stone but made of plasma and delayed photons. Now for your quirky tidbit, something a little odd, but it helps you stay awake just long enough to appreciate the scale. There's a long-running habit in astrophysics of calling certain galaxies normal, even when they host supermassive black holes doing bizarre things on scales that would ruin your entire day if they happened in your neighbourhood. Normal galaxy, they'll say, meaning not currently blasting as an AGN, as if having a 4 million solar mass gravitational abyss at the centre is just normal. The universe's baseline is already absurd. You only call it exciting when it screams. Joke 2. Astronomers will look at an enormous black hole and say, seems quiet, like they're reviewing a cafe. 4 stars. Nice ambiance, mild flaring. And here's your open scholarly debate phrase drifting in with the cool air of unresolved questions. Historians still argue whether the AGN duty cycle, the fraction of time a galaxy's central black hole spends in an active luminous phase, is primarily governed by large-scale galactic events like mergers and bars, or by smaller-scale, local processes like turbulence and feedback near the centre. The debate matters because it decides how you interpret Sagittarius A star. Is it quiet because the galaxy isn't delivering fuel on large scales, or because the inner flow rejects fuel through winds and inefficiency even when material is present? You let that question hover like a mobile over a crib, slow, swaying, unresolved. Because the truth might be both. The Milky Way is not currently merging with a big gas-rich galaxy in a way that would dump huge amounts of fuel inward. But the central region still contains gas, winds, and clumps. The inflow may be intermittent, the inner flow may be inefficient, the system might be starving on the outside and picky on the inside, an unfair combination if you're a black hole trying to build a reputation. And Webb's data lets you probe the picky on the inside part. The flickers and lags and flare frequencies speak the language of inner physics, particle acceleration, magnetic reconnection, cooling times. This is the physics you can carry to other galaxies when you don't have the luxury of close-up star orbits. You also begin to feel a subtle emotional shift. Sagittarius. A star becomes less of a monster and more of a lab, a nearby case study. It's still dangerous in reality, sure, but in your story it's a controlled danger. Danger viewed from a safe distance, turned into numbers and patterns and debates. Joke 3, quietly. You can't visit Sagittarius A star, but you can absolutely visit its spreadsheet. And as you continue forward, you sense what's coming next in the glide. If Sagittarius A star is a quiet phase black hole that still flickers and occasionally flares, then the Milky Way's past might not have been so quiet. There are hints, giant structures, leftover signatures, that the centre has burped before, maybe not long ago in cosmic terms. So you keep walking down that museum hallway of black holes, and you find a door labelled the Milky Way's past outbursts. The handle is warm, the room inside is dim, and you step toward it without rushing. You step through that door you just felt, the one labelled with the Milky Way's past outbursts, and the room inside is not loud. It's the kind of quiet that comes after something big already happened, the kind of quiet where you can still smell smoke even though the fire is gone. Your mind glides over the galactic centre again, but this time you're not looking for the present flicker. You're looking for scars. You're looking for leftover shapes that don't make sense unless the quiet black hole used to be less quiet. Because Sagittarius A star is dim now, yes, but dimness can be a phase, not a personality. You imagine the Milky Way as an enormous city seen from far above at night. Most neighbourhoods glow gently. The downtown, your galactic centre, should be just another bright knot. But there are faint, enormous structures rising above and below the plain, like the city once had 2 colossal searchlights pointed into the sky. Not searchlights exactly, something bigger, older, and harder to explain away. This is where you meet the evidence that feels like a cosmic aftertaste. vast bubble-like lobes extending from the Milky Way's centre, often discussed as remnants of energetic events in the past. Whether they come from star formation activity, a central burst, or from the black hole itself, they suggest the galaxy's heart has not always been a calm, underfed tenant. Mainstream historical fact, laid down gently so it doesn't jolt you. In 2010, researchers analysing gamma-ray data reported the presence of enormous structures now widely known as the Fermi bubbles, extending tens of thousands of light-years above and below the galactic plane. Their discovery brought a new urgency to the question of what the Milky Way's centre did in the recent cosmic past, because creating such large energetic features likely requires a significant injection of energy, either from intense star formation-driven winds or activity tied to Sagittarius A star itself. And now you feel the shift. Webb's shock in the present, frequent twitchy flares, sits on top of a deeper story where the centre might have had episodes of far greater energy output. Not necessarily a quasar-level blaze, but something strong enough to sculpt the halo. You let the imagery be slow and sensory. You picture the galactic plane as a thin, luminous band. Then you imagine two ghostly, symmetrical bubbles rising above and below it, like pale lanterns in the dark, but enormous. The kind of thing you would never notice if you were inside the galaxy and not looking with the right wavelengths. The kind of thing you only recognise once someone points it out, and your brain says, "Wait, that's there?" And then you turn the question towards Sagittarius A star again. If the black hole is quiet now, could it have been louder in the recent past? Could it wake up again? You don't mean wake up as in suddenly eating the sun tomorrow. Please keep breathing. You mean wake up the way a system can shift states. A larger inflow of gas, a change in feeding conditions, a new clump of material spiralling inward, a change that turns the simmer into a brief boil. Webb's flares show you that the inner engine is capable of rapid, energetic events, even when the average output is low. That's a hint that the black hole is not dead, it's idling. Joke 1. Soft. Sagittarius. A star isn't asleep. It's just doom-scrolling quietly in infrared. Now you drift through possible sources of a larger past outburst. One scenario is star formation, massive clusters near the centre, producing winds and supernova that collectively blow bubbles. Another scenario is black hole activity, an episode where Sagittarius A star accreted more material and launched outflows, winds or jets, that inflated the structures. The truth could be mixed. The centre is a complicated place, and the galaxy rarely gives you clean single-cause narratives. And this is exactly where your open scholarly debate phrase belongs, because people really do argue about this. Historians still argue whether the Fermi bubbles and related structures are best interpreted as evidence of a past Sagittarius A star outburst, or as the product of sustained nuclear star formation, because both processes can inject energy and drive large-scale winds, and the observational fingerprints can overlap. The debate persists because it's hard to rewind a galaxy and watch the event happen again. You let that uncertainty be calming instead of frustrating. It means the story has depth. It means you're not reading a finished script written by the universe. You're watching scientists trying to reconstruct a past event from its echo. Now for your quirky tidbit, something slightly offbeat to keep you smiling while your eyelids get heavier. The idea of a burping black hole has become an affectionate piece of astronomy slang. It's irreverent, yes, but it captures a real behaviour. Accretion can be episodic. The black hole can remain dim for long stretches, then briefly brighten as it gets a new gulp of material. In your imagination, the centre of the galaxy is like a creature that occasionally clears its throat loud enough for the whole halo to hear. Joke 2, the Milky Way centre has had a few "are you up" moments, and the halo still remembers. Now you connect this back to Webb's present-day shock. If Sagittarius A star is flaring frequently, if it's constantly rearranging magnetic energy and accelerating particles, then the system is not static, it's dynamic. and dynamic systems are the ones that can change state when the conditions shift. Today's flickers could be the small-scale version of processes that, with more fuel, would scale up into something much more dramatic. You picture the accretion flow again, thick, hot, magnetized. If more material arrived, say, a denser stream or clump from the surrounding environment, the flow might not become a neat thin disk immediately, but it could brighten, drive stronger outflows, and produce more intense multi-wavelength activity. The quiet center could have active seasons, but you stay grounded. The timescales matter. The galaxy's gas supply changes slowly. A true major outburst might be rare. Still, the evidence in giant structures suggests it's not impossible, and the present-day flickering suggests the engine still works. Joke 3, barely above a whisper. It's like owning an old car that usually idles quietly until you find out it once did a cross-country race, and you're suddenly listening to every little rattle like it means something. You keep your narration gliding, no fresh intro, just a continued soft walk. The past outbursts debate leads naturally into future mood. What would it take for Sagittarius A star to become brighter again? A significant increase in the inflow of gas, changes in the inner flow's efficiency, perhaps interactions with passing gas streams, perhaps the long-term evolution of the central region's stellar winds and clumps. And Webb's role in this is subtle but important. By characterizing the present variability in detail, Webb helps establish a baseline. It tells you what normal quiet looks like when you can actually see the flickering. That baseline is what you need if you ever want to recognize a genuine shift in state. If someday the center begins to brighten in a way that's sustained rather than twitchy. You let that idea soften into a lullaby thought. The galaxy has moods, and you're listening to tonight's mood carefully. And as you drift onward, you feel the next step waiting. The practical future of this story is not one dramatic conclusion, but continued watching. More Webb monitoring, more coordination, and the slow, patient hope that the black hole will flare again at just the right time to answer the questions it raised. You keep drifting forward from the Milky Way's old scars, the giant bubbles and the arguments about what inflated them, and you land gently in the only place science can really live, the next observation. Not the next headline, not the next dramatic sentence, the next stretch of patient watching, where you wait for Sagittarius A star to do the thing it does when you're paying attention, flicker, flare, and refuse to explain itself clearly. You're in that quiet late-night mindset now, the one where waiting feels natural. You understand, on a sleepy level, that a black hole doesn't perform on command. It doesn't care about your schedule. It doesn't care about grant deadlines. It doesn't even care that you're trying to fall asleep to it, which is frankly rude, but also on brand for a supermassive gravity well. So you picture the observing campaign like a kind of vigil. Webb is your lantern, held steady. But it's not the only lantern. If scientists want to turn weird flares into understood physics, they don't just need more Webb time, they need coordination. Because a flare that looks like a single event in infrared might be part of a larger multi-wavelength story. Infrared might show the first brightening. X-rays might spike if particles get especially energetic. Radio might respond later if an expanding blob becomes transparent at longer wavelengths, or if outflows carry energized particles outward. You imagine it like a relay race. One wavelength hands the baton to another, not because the universe is being poetic, but because different emissions come from different particle energies and regions. If you can catch the baton handoffs, you can reconstruct the race. Mainstream historical fact settles in here, calm and dependable. In 2015, the LIGO detectors made the first direct detection of gravitational waves, and one reason that moment mattered so much is that it cemented the modern habit of multi-messenger and coordinated observing. The idea that you don't fully understand a cosmic event by looking with one instrument alone. Even when you're not using gravitational waves for Sagittarius A star, the mindset carries over. Synchronize your eyes, compare your signals, and let different instruments constrain different pieces of the same physical process. So you watch scientists do the practical thing. They plan monitoring windows. They choose cadences, how often to sample the light, because cadence can be everything. Sample too slowly and you miss the flare's sharp rise. Sample too quickly in the wrong way and you waste precious time or drown in data that's hard to interpret. It's like trying to catch a firefly on camera. You need the right shutter speed, and you need the patience to sit still long enough that the firefly forgets you exist. Joke 1. Soft. Astronomy is the only hobby where just keep staring is both the plan and the funding request. You keep the tone relaxed as you move through what case closed would even mean here. In a turbulent, magnetized flow, there might not be a single closing argument, but there are stronger and weaker conclusions. A strong conclusion would be something like, repeated flares show consistent time-lag behavior across bands. Spectral evolution matches a particular cooling model. The inferred emitting region size and timescales line up with orbiting hotspots at a specific radius, and the statistics of flare frequency match simulations of magnetically driven turbulence. Not one flare, but a population. Not one night, but many. The kind of dataset that makes even stubborn skeptics soften, and that's why the next observations matter. You need repetition. You need variety. You need enough events to separate pattern from coincidence. You picture the campaign as layered. Some observations aim for long continuous monitoring to catch many flares and characterize the baseline variability. Others aim for rapid cadence during predicted active windows, because sometimes the black hole seems more twitchy on some nights than others. And in the background is the hope that nature will cooperate just enough to give you a flare at the right time when multiple observatories are watching. But the universe has a petty streak. It loves flaring when you're not looking. Joke 2. Sagittarius. A star has the energy of a cat that only does something cute when your phone is at 2% battery. Now your open scholarly debate phrase arrives, fitting this section's theme of planning and patience. Historians still argue whether the most decisive scientific progress comes from grand planned campaigns or from opportunistic surprises, because sometimes you schedule a beautiful program and the universe gives you nothing, and other times you glance at the data on a Tuesday and discover the thing you weren't even searching for. With Sagittarius A star, researchers debate how much to bet on steady monitoring versus rapid response flexibility, because flare physics rewards both persistence and luck. You keep drifting through the practicalities without turning it into a lecture. You keep it sensory. You imagine the scientists in dim offices, screens glowing softly, watching a line creep across time. You imagine the moment a flare begins, just a small uptick, and someone's body posture changes. They sit straighter, they stop breathing for a second, they message collaborators, they check the timestamps, they check if other instruments are also watching. It's quiet excitement, the kind that feels like holding a cup of hot tea and realizing it's warmer than you expected. Now for your quirky tidbit. This one is for the sleepy part of your brain that likes ritual. Astronomers have a long tradition of naming coordinated observing runs with slightly dramatic nicknames, as if the cosmos is a band going on tour. It's not fringe science, it's just culture. A way to make months of scheduling feel like a quest. And in the Sagittarius A star world, that quest has a particular flavour, because you're trying to catch a flickering thing that doesn't announce itself, in a crowded field full of other flickering things. Joke 3, gentle. It's like trying to hear one person whisper at a party where everyone is also whispering, and half the guests are wearing glitter. You let the narrative glide into what the next dataset might answer. If Webb continues to see frequent infrared flares, scientists can measure the distribution of flare energies. How many small ones versus big ones? They can look for correlations. Do stronger flares show different lag structures? Do flares cluster in time? Are there nights when the baseline variability ramps up, suggesting the inner flow entered a more turbulent episode? They can also test whether quasi-periodic hints persist. If a rhythm shows up again and again at similar timescales, it becomes harder to dismiss as chance. If it comes and goes, it might be a transient feature, like a short-lived hotspot or a temporary magnetic configuration. The universe might not have a metronome, but it might have brief moments where the beat is audible. And then there's the broader coordination. Compare with radio observations to see if later time emission rises, supporting expanding blob or outflow scenarios. Compare with X-ray monitoring to see whether the most energetic flares have high energy counterparts, which would constrain particle acceleration efficiency. Compare with polarization measurements, where available, to probe magnetic field geometry, because polarization is one of the most direct ways to test how magnetized the emitting region is. In a story dominated by magnetic knots and reconnection, polarization is the quiet witness who can finally testify. You keep your voice low and smooth because this is still bedtime storytelling. But you let the waiting become a calm suspense. You're not rushing to conclusions, you're watching a system in motion, and you begin to feel the shape of the ending approaching. Not a hard ending, but a soft one. Because after the next observations, after the planned campaigns, after the arguments and refinements, you will arrive at a gentle plateau. What Webb showed that surprised scientists, what remains uncertain, and how it feels to stand at the edge of the Milky Way's darkest heart while still being, in the end, just a warm human in a cool room. You keep drifting forward, prepared for the final section's soft landing, the kind where the story doesn't slam shut, it exhales. You keep drifting forward from the long vigil of Section 19, the planning, the coordinated watching, the hope that the next flare will arrive when the right instruments are awake. And now you find yourself standing at an edge that isn't really an edge. It's more like a boundary your mind draws so it can feel safe. Here is where understanding lives, and there is where the abyss begins. You stand there anyway. You're still in second person, still present tense, still moving through the Milky Way center as if it's a quiet city at night, and Sagittarius A is the unlit building everyone keeps orbiting. The building doesn't turn its lights on, it just shifts behind the curtains, and thanks to Webb you've noticed the shifting. So what exactly shocked scientists? Not in the tabloid sense of jaw-dropping cosmic monster revealed. In the truer, calmer sense, the supposedly quiet black hole is constantly alive with motion in its immediate environment. The infrared emission doesn't just sit there, it flickers repeatedly, with a baseline jitter that suggests ongoing activity, and with flares that pop often enough to feel like a system that is not resting, only idling. The shock is that the idling has texture. It's the difference between thinking a room is empty because it's dark, and then realizing you can hear soft footsteps and the occasional clink of glass. The room was never empty. You just didn't have sensitive enough ears. Webb's stare gives you those ears, and it shows you that the inner accretion region, whatever shape it truly takes, reorganizes itself again and again. Magnetic fields tangle, particles accelerate, electrons lose energy and shift their glow across wavelengths. You see timing lags that suggest evolution, propagation, cooling, maybe expansion. You see behavior that is too frequent and too structured to dismiss as a rare anomaly. And yet, in the same breath, you feel the humility that comes with any good dataset. This is not a solved mystery, it's a better question. Because every potential explanation you've held, hotspots orbiting close in, magnetic reconnection snapping like cosmic Velcro, turbulence and shocks bumping around in a thick flow, outflows carrying energy away, can reproduce parts of what Webb sees. And the deeper you go, the more you understand why scientists argue so politely and so fiercely. The system is not simple, it's layered, it's crowded, it's changing while you watch. You can almost hear the argument loop from Section 16 humming like a ceiling fan. Is that periodicity real? Is that lag intrinsic or an echo? Is the flow disk-like or mostly coronal? How much is driven by external winds versus internal magnetism? No one is wrong for asking. The black hole's neighborhood rewards suspicion, so you stand at the edge and hold the most honest summary you can. Webb didn't solve Sagittarius A star. Webb made its quietness impossible to misunderstand. Quiet isn't empty. Quiet is subtle. Quiet is full of information you can only see once you stop shouting with your own instrument noise and start listening. And because your mind is a mind, it tries to stitch this into the larger tapestry. You remember the old historical backbone, Kepler and Newton giving you orbital inference, Einstein giving you the deep gravity framework, the 20th century teaching you to read the sky and radio, the 1960s teaching you that quasars are black hole feasts, the late 20th century refining accretion theory, and now Webb adding a new intimate kind of surveillance, infrared patience, long enough and sensitive enough to catch the fidgeting in the dark. You also remember the quirky pieces that kept you smiling, Sagittarius, a star named with an asterisk like a footnote, gold on Webb's mirror like jewellery turned into science, the galaxy's centre behaving like a quiet roommate who somehow reorganises everything at 1:37 a.m, the cosmic weather metaphor, the messy drawer of speculative companions, the scientific ritual of just a quick reanalysis that eats half a year. All of that human texture sits beside the deep physics like a warm blanket thrown over a cold machine, and then you let yourself accept what remains uncertain. The exact geometry of the inner flow, how puffed up, how lopsided, how magnetically structured. The exact mechanism behind the most common flares. The degree to which any quasi-rhythm encodes orbital motion versus statistical patterning. The extent to which the neighbourhood stellar winds modulate the supply line. The relationship between today's flickers and the evidence of bigger past outbursts, the bubbles in the halo, the scars that hint the centre once cleared its throat more loudly. You don't need certainty to feel wonder. You only need the sense that the galaxy is alive, that its heart is not a still photograph but a moving system. And now, as promised, you begin the wind down, slowly, softly, letting the vocabulary soften and the sentences lengthen, letting the ideas become less sharp and more like drifting mist. You imagine yourself stepping back from the galactic centre, not with a sudden cut, but with the gentle backward motion of a boat easing away from a dock. The flickers you saw become smaller in the distance, but you can still feel their rhythm as a kind of hush in your chest. The stars around Sagittarius, a star, keep looping in their patient ballet, their arcs so reliable they can weigh an invisible monster without ever seeing it. The dust lanes close like curtains again, but now you know they're only curtains, not walls. Webb remains out there, quiet and cold and steady, holding its golden mirror toward the dark, listening in infrared to a place that will never speak in words, and you, here in your room, let that image become a comfort instead of a threat. The universe is enormous and indifferent, yes, but it is also readable in small, gentle changes, in flickers that repeat, in delays that reveal distance, in patterns that slowly emerge when someone has the patience to keep watching. Your breathing slows as you picture the Milky Way as a soft river of light again, and you allow yourself to drift along it, away from the crowded centre and back toward the calm outskirts, where your little planet spins quietly, doing its ordinary miracle of night. You feel the fan hum if you turned it on. You feel the weight of your blanket. You feel the safety of distance, the kind of distance that lets you be curious without being consumed. And as the final imagery fades, you let Sagittarius A star become what it truly is for you tonight. Not a mouth, not a monster, not a doom prophecy, but a quiet, restless heartbeat far away, measured by patient instruments, argued over by stubborn humans, and held in your mind for a few minutes before sleep takes it and smooths it into dream.